Welcome to APEC Open Mic. It's November 11th, and happy third birthday, APEC. I am your moderator, Tim Ventura. I want to give a big thank you to everyone for joining us on this call. A giant thank you to everybody for supporting us for 3 long years, covering all sorts of topics in emerging propulsion technology, UAP technology, emerging energy technology. We have just run the entire gambit. It is so exciting, and we are so appreciative for your guys' support, patience, and just helping us move everything forward. So thank you, and as well as thank everyone watching us on YouTube. As a reminder, today's session is for open discussion and ad hoc presentations. We don't have anything big planned for you, but we do have some folks who want to present today. Curtis Horn mentioned that he wanted to share some things. Sean Logan has some updates, and Andrew Arugama has some updates as well. We also have other folks who may pop in and just share things with us. I am excited to get them started. I do want to give you a couple of quick reminders first, though. You can view conference replays, details, and speaker info for our scheduled conferences on our website at altpropulsion.com. Please pop by our YouTube channel as well and subscribe to that if you haven't already. During today's ad hoc presentations, try to save those questions for after the presenter finishes, if possible. Again, we're a little bit more mellow and flexible, right? Because this is the ad hoc presentation. But when we interrupt people, they lose their train of thought. I know at least I do. And so try and save those for after if you can. You can raise your hand in Zoom using Option Y on Mac or Alt Y on Windows. You can also type your questions into chat. Again, we're not going to be firm on hand raising during open mic unless things get chaotic. So let me encourage you to jump in if it feels appropriate. We're going to try and keep things focused on the core topics of the alt propulsion community, though. That is one of our focus areas. So again, we do have some ad hoc presentations, and we will get started with those. And again, happy third birthday, APEC. Okay, well, everybody, I'm going to remove the spotlight, and I will put this on gallery view, allow everybody to unmute themselves. So, Sean, let me see. You had a presentation that you wanted to do, right?
Yeah, should I share my screen?
Yeah. And guys, is it okay if we start out with Sean Logan?
Sure.
Okay, yeah, let's do it then. Okay, so. Okay. Sean, why don't I spotlight you for everybody? And I would say go for it. You can do a screen share if you want. There we go.
Okay. Can you see that?
Perfect.
Okay. Well, thank you for allowing me to present. Today, we're going to learn about hyperdimensional light. If you've studied linear algebra, you may be familiar with the concept of a hyperplane or a subspace. That's when, for example, here's a simple example. You have a vector space. This is a 3-dimensional vector space. And then within that, you have a subspace, which is isomorphic to fewer dimensions. So here we have a plane, a 2-dimensional plane within a 3-dimensional space. But this idea extends to higher dimensions. You could have a 7-dimensional space with a 3-dimensional subspace within it. So there may be some flatlanders living on this plane here, going about their flatlander business, completely unaware that their entire universe is actually contained within a higher dimensional space. Until something happens in the 3D space, which intersects their 2-dimensional space. For example, maybe in the 3D space, there's an isotropic antenna that's giving off spherical wavefronts. And when those spheres intersect the plane, they create a circular cross-section. So the flatlanders living in the plane, they would see these concentric circles spreading out, but they would have no idea where where this was coming from or why this was happening. And likewise, we in our three-dimensional space might see a three-dimensional cross-section, as it were, of higher dimensional objects entering into our space. We might see concentric cylinders of increasing length rather than circles. If, for example, a four-dimensional object were to enter our space like this. So let's build something that's actually shaped like this if we want to try to interact with a higher dimensional space. And we're going to excite the central element, the long skinny tube in the center. This is just made of mild steel, just concentric cylinders. And we're going to charge the central element negatively and then vary the charge on that with respect to time. If this was an antenna, you would call the piece of metal that's hooked up to your amplifier, you'd call that the driven element. And the other pieces of metal that are just sitting in the space nearby, those would be called parasitic elements. But we're going to operate this at a very low frequency compared to the length of this, because we want to vary the charge on the entire thing all at once. So when something is charged, a condition exists in the space around it called the Coulomb potential. And it's possible to compute this for certain geometries so we can see what it looks like. A piece of pipe is cylindrical, so we'll set it up in cylindrical coordinates. And what we're going to do is just take a plane and slice through the middle of the pipe lengthwise and compute the Coulomb potential in that plane, because the pipe is symmetrical. So you could rotate this plane around through any angle and it would always look the same. So we don't need to calculate everything in the whole space. It's enough to just do this plane and then we'll get an idea of what everything looks like. So this is what it looks like. If you want to see the equations or look at the code that I use to calculate this, you can download it from my website. I'll give the address at the end of the talk. But this is what the Coulomb potential of a charged pipe looks like. You can kind of see the edge of the pipe is where the white stuff drops off. White indicates high Coulomb potential. And then if you take the gradient of this, which is the derivative with respect to space in each of three spatial dimensions, that gives you the electric field. And so you can see on the electric field, it's actually very low inside the pipe. It's actually 0 at the center. And it's high right at the edge of the pipe on the outside. Whereas the Coulomb potential is very high inside the pipe. It's one of the many ironies of history that early electrical researchers like Faraday and Maxwell, they considered the Coulomb potential and the magnetic vector potential to be the primary physical reality when it comes to electrical phenomena. And things like the electric field and the magnetic field were derivative quantities. I mean, the electric field is literally the derivative with respect to space of the potential. But when Maxwell's equations were written in the Heaviside vector form, you only see electric field and magnetic field. You don't see the potentials at all. And people got carried away with the electric field and the magnetic field because those represent actual Newtonian forces that push on things and do stuff. And they got this idea somehow that the Coulomb potential was not actually a real thing, that it did not represent anything going on in physical reality. It was just an abstract mathematical concept, but it didn't really exist. And scientists thought that way for about 100 years until these guys came along in 1959, Yakir Aharonov and David Bohm. And they pointed out, well, if you look at things from the point of view of quantum mechanics, the Coulomb potential is actually the only real thing. and the electric field only appears as a limit in the classical limit. And they wrote this paper, Significance of the Electromagnetic Potentials in the Quantum Theory, where they proposed some experiments that you could actually prove that the Coulomb potential exists. That, and their experimental setup was you take a pipe, you charge it up, and you shoot electrons down the length of it, and the Coulomb potential will affect the electrons. And people have done these experiments several different times in different ways, and this is known as the Aharonov-Bohm effect. It's now a well-known thing that the Coulomb potential is real. It does exist in physical reality. So if you have a pipe that's charged up, there's an energy field, or whatever you want to call it. There's something going on inside the pipe. Here's another way you could think of the relationship between these two quantities. If you were to think of this, the white stuff is where the Coulomb potential is high. That's like, it's very tall. And the red and purple is like a lower altitude. You could think of it as a mountain. You're climbing a mountain. And as you go up the mountain, your altitude at whatever point you're at is your Coulomb potential. But the steepness of the mountain at that point is your electric field. So you could think about, say you're at the top of a tall mesa, it's flat on top. That's what it's like inside the pipe. Your Coulomb potential is very high, but since it's flat, your electric field is zero. So you can have high Coulomb potential in places where the electric field is zero. And now what we're going to do is vary the Coulomb potential with respect to time. We're going to vary the amount of charge on this pipe. And we're going to do it fast enough that it's like a vibration. It's like a sound wave vibrating something. And one way you could think of it is that the space itself is vibrating. You could think of our space, it's like a membrane, like the skin of a drum. And if you whack the drum, it's going to vibrate. And this membrane is it's something like a hyperplane. It's like a subspace within a higher dimensional vector space. If you strike a drum, the head of the drum will vibrate. But the sound waves don't just stay on the drum. They spread out into the air in the room all around you. And in a similar way, if you whack space by varying the Coulomb potential, the waves of the Coulomb potential changing spread out into the higher dimensional space, which our space is nested within. These waves, they're not like normal radio waves. They don't travel from me to you at the speed of light. They exist in a higher dimensional space. And what we see is a three-dimensional cross-section of them. To us, it's more like a standing wave. Just like these flatlanders might see circular cross-sections of a spherical wave passing through their space. We're going to see a cross-section of a higher dimensional wave going through our space. So this structure, these concentric cylinders, it acts like something analogous to an impedance matching device, which allows there to be this coupling between our space and this other space. You may know that when the impedances of your source and your load are not the same, then when you send your waves to the load, they'll bounce off, they won't go into it. But if you make an impedance matching device that couples the two impedances together, then when you send your waves through, they go to the load and they don't reflect. So we know from Maxwell's equations that when you have a time varying electric field, that gives you a magnetic field. And the magnetic field is characterized by stuff spinning around in a circle. Magnetic fields always form closed loops. And the electric field is defined as the gradient of the Coulomb potential. It's the derivative of the Coulomb potential. So you might ask yourself, what happens if you vary the Coulomb potential with respect to time, especially in a volume of space where there's no electric field? What is that? Does that mean anything in physical reality? Well, yes, it does. There is something that is associated with the time varying Coulomb potential. And like a magnetic field, it is characterized by things like a circulation or a vorticity, stuff going around in a circle. But unlike a magnetic field, it does not form a closed loop. It actually forms a helix or a corkscrew kind of shape. And so we've got this pipe here running down the center of this structure. And as we vary the charge on it up and down, this stuff starts to wrap around the pipe and spiral up it. And it actually extends past the end of the pipe. And you also see it inside the pipe coming out of the center. It's a corkscrew shaped, it's helical. This helical stuff, it doesn't travel away from the pipe at some velocity. It just sits there rotating, like some kind of a standing wave. And it can interact with coils that are wound on an iron core if the iron has a hole in it. It's something related to a magnetic field, but it's not the same thing as a magnetic field. And it also interacts with living things, plants and animals. It seems to be related to life, processes involved with life. So what do we need to build in order to vary the charge on this pipe? We could make something as simple as a class A amplifier. And all we're going to do is we're going to connect the positive terminal of the voltage that's powering this thing. We're going to ground the positive. And when I say ground, I mean connect it to the earth, like clamp it to a water pipe buried in the ground. If you do that, then any point in the circuit that's at a lower voltage is going to be charged negatively. You could even add a second voltage, as I've done here, to push everything negative. Because what we want to do is we want to vary the charge, but we want to always keep it negative. We don't ever want to let it swing positive. You could sort of think of this as it's like a flywheel. It's like you're pushing a flywheel. And as long as you keep it negative when it's varying, that's like you're pushing the flywheel clockwise. And you keep pushing it in the same direction, and it gets going, and it builds up momentum, and it will keep spinning even when you stop pushing it. Here's an even simpler and possibly more effective way to do it. This is a circuit that runs on DC, and all you've got is a coil, your pipe, and then some kind of switching mechanism. That could be a spark gap, a vacuum relay, a mechanical commutator like the distributor cap in an old car. And the way this works is, the way I built it was with a vacuum relay instead of a spark gap. It runs on DC, and what happens is when your switch closes, current starts flowing through the coil. And because the coil has inductance, it takes a few seconds for the current to ramp up. First a little bit of current starts flowing, then some more, then some more. And as the current ramps up, you get a magnetic field spinning around the coil. There's actually energy being stored in the magnetic field. And then when you break the circuit, when you open the switch, all the energy that's stored in that magnetic field slams into this pipe in the form of voltage. And you get this very sudden, very sharp spike of high voltage. So you can see that the top graph here is showing your current. It starts ramping up when the switch closes. And then when your switch opens, when you break the circuit, then you get a spike at high voltage. And I was using 100 volts DC to run this thing, and I was using a vacuum relay as a switch. And my choke was about 20 Henrys. And from 100 volts DC, the coil was kicking out about 30 kilovolts on these spikes. So this might be a good approach to try at first, because this is like, it's like the thing is like a big bell, and you're just hitting the bell with a stick. You're just whacking it and letting it ring at whatever frequency it wants to, whatever its natural resonant frequencies may be. And I've been told that if you were to do a Fourier transform, an FFT on a spike like this, a spike contains all frequencies. It's a very wide band signal. So there's a vacuum relay I used, and the choke, and a timing circuit to turn the relay on and off. There's a number of different ways you could build these things. The particular ratio I used for this one was the golden ratio. Euclid called that the extreme and mean ratio. He talks about it in the Elements of Geometry. So if your physical dimensions are based on a certain ratio, then the waveform that you give it is, you want that to also contain frequency components that are in the same ratio. So here's a plot of two angular frequencies that are in the ratio of 13 to 8. That's a pretty good approximation of the golden ratio. If you look in old astronomy textbooks, you might find a picture of this. They used to call this the Rose of Venus. And what this is it's like you're up above the plane of the solar system looking down. The sun is in the center, and Earth and Venus are orbiting the sun. And every couple of days you draw a line from Earth to Venus. And it turns out that 8 Earth years is 13 Venus years. And if you draw lines between the two planets every couple of days, you draw this picture. I wrote some code you can find on my website where you can put in different ratios and see what they look like. I found it's more helpful than looking at signals on a scope. You know, this could be 13 kilohertz and 8 kilohertz added together linearly. But on a scope, it's not immediately obvious what the relationship is. But if you look at it plotted in a circle like this, it's more clear what's going on. So this ratio has an interesting property. It has a lot of unique mathematical properties, but the one I'm interested in when it comes to waves is that consecutive integer powers of this ratio, when added together, gives you the next power. So for example, we'll call this ratio alpha. Alpha to the -3 plus alpha to the -4 equals alpha to the -2. It's basically, the idea is when you heterodyne two waves and you get sidebands, those are the sum and difference frequencies. If your original two waves, if their frequencies are in the golden ratio to each other, then the sidebands that you get will form a geometric sequence in the frequency domain with the original two waves. And then if you feed your sidebands back into your mixer, you have some kind of feedback or recursion going in your circuit. You'll build up this whole geometric sequence of frequencies. And the sum of any two of these frequencies is the next one, and the difference between any two of these is the previous one. So here's a prototype I built. This was built around a 3-inch length of pipe in the center. And the outer rings are pieces of just 16 gauge mild steel. Just cut out rectangles and roll them up on a sheet metal roller and weld the ends together to make the cylinders. This is what the dimensions look like algebraically, where if you take the length of the center element, then all the other elements are just powers of the golden ratio multiplied or divided by that length. And the envelope of this shape, if you were to draw a curve that just touches each one of these rings, that curve is going to be a hyperbola. If you rotate the hyperbola around one of its asymptotes, you get this shape here. It's called a hyperbolic horn, or Gabriel's horn, or the acute hyperbolic solid, the hyperbolicum acutum. So what we're basically doing is we're just taking cylindrical slices of this funnel shape. This is a shape that exists in nature. It's the shape of a tornado or of a vortex in water. And the hyperbolic horn is also used in acoustics. You might see it on a loudspeaker on a stage. It's an acoustical impedance matching device. That's what it looks like. That's an early prototype I made out of steel foil. There's a bigger one. It's made out of 16 gauge. And if you want to, you can look at my website and see animations of this and see the equations where it comes from. It's if you wanted to talk to somebody on the other side of the galaxy, but you didn't want to wait a million years for your radio waves to get there, this is one way you could do that, because the waves that this interacts with are going outside of our space. It's a little unusual. Oh, here, that's all I have to say. I'll put this link in the chat too.
Sean, thank you. Thank you, sir. Okay, let me do this. I am going to stop your sharing if I can. There we go. And I have unspotlighted you. We have a full house. Look at all these folks. Look at all of these folks. This is amazing. Thank you, everybody. Thank you so much for joining us. Does anybody have questions for Sean? And again, let me see.
Do we
I
just
believe it's
ask our questions out, Tim?
yeah. And I think it's Alt Y on Windows, Option Y on Mac. If that's yep, I believe that's the key combination. If you guys want to raise your hand, or Drew, if you have questions, just go for it.
Sure. I'm just curious. You say this thing is like a transmitter, receiver, whatever. How do you know you're going to get information back? I mean, how do you know you transmitted something, and how do you know where it went, or if you ever got anything back?
That's a really good question, and I don't have a good answer for you. All I can say is that if you vary the charge on that central element, you are gonna interact with waves that exist outside of our space, and there are people up there listening.
Okay.
Okay.
How do you know that?
Well,
Are you just guessing there's somebody up there?
I don't really want to talk about that, but
Oh,
there are people who are listening.
Okay.
I thought I mentioned to Sean one of your DC pulse circuits was feeding that tube with flyback. Reverse polarity flyback was hitting that tube in one of your circuits there with the DC switch spark gap.
Yeah, it's just a single coil.
Yeah, that's a flyback generator.
Yeah, it's basically a switching mode power supply. It's like a very simple switch mode power supply.
You put the tube in series with the coil, it became part of the flyback event. When you forward charge that with DC and turn off the switch, it reverse polarities, including the tube. Since it's in series with the coil, it will also reverse its polarity on the off cycle. The on cycle is your forward DC voltage. And then when you turn it off, it reverses polarity, whatever's in that circuit, including the tube, which was in series with your coil. The coil will reverse polarity. And
yeah, you can.
The tube.
You know, I put the coil and the switch. I put the coil on the negative side of the circuit from the switch. If you put the coil on between,
you're switching the negative. You were switching the negative.
You can, the way I have it wired, you're gonna get a spike of negative voltage. If you switch the position of the coil and the switch, you'll get a positive pulse, but it won't work properly if you do that. You want a negative pulse.
Right. It's the flyback. It's a negative. It flips the poles on the inductor when it flies back.
Mike, your background looks strangely familiar.
Right?
Have I seen that on TV?
Most likely. Took me a while to pick it out. I like it too.
Yeah, no, it's good. You know what? It'd be
Star
cool
Trek.
if the stars. It'd be cool if the stars moved.
I was thinking that. Yeah. Got to find animated GIF.
Yeah, yeah. Hey, let me go to Norman. Norman, go for it, sir.
Okay, am I on
There
all
we
right?
go. Yep. Now we can hear you.
So yeah, I'm listening to this. I actually received email about this and wasn't sure exactly what it was, and I understand that this is alternative propulsion that we're not normally using, and it's kind of taking sci-fi to reality. Are we trying to do that? And what he was talking about kind of reminded me a little bit of Lenz's law on with working with the voltage and with metallurgy like copper. I'll tell you kind of the perplexion that I have with this. I've been doing this for 8 years. I've done about 6,000 experiments. I've built 5 prototypes, 4 of them that I've had fly levitation. And with the frequencies, I'm sorry, but the frequencies don't fly everywhere. You have to hit a specific frequency, a minimum, and then the frequencies go up from there mathematically in regards to what you want it to do. I have been working instead of linear, I've been working in tangential field with centrifugal forces on charged particles. And I'm not stuck in a pipe. I actually went outside of that and I went the opposite direction where I'm actually working with charged particles that are bouncing off each other to do what, in the Southern expressions, to do what they say can't be done. And so I'm kind of, I talked to the White House this summer by invitation and told them what it was that I had been doing, and this doesn't sound like much difference to me. We need to expand our vision. I actually plan on having my prototype ready springtime to put a chair on. That's where I'm at.
Well, so Norman, if it's okay, do you have videos and stuff of these experiments?
Oh yeah,
I mean,
yes, I do.
Well, I mean, what? Yeah, I would say, maybe we should probably finish up questions for.
I'll let you guys go. Yeah, I wanted to recording on this and get back with you because I've been talking to Musk about this for a week now. And I'm just trying to find out where you guys are at and then talk a little bit more.
Yeah, I would say it would be wonderful to have. You're talking about lens levitation, right? And I know Boyd Bushman was really into that.
That's part of the backbone of what I do, but I've covered 7 different laws of physics doing what I'm doing. He's just part of it.
Well, it would be wonderful to, I would say bring those in. We could play those videos on air. Usually we turn the sound off so we don't hit YouTube's copyright stuff. But that would be awesome to just kind of go through those and see, what you've been working on, as much as you're willing to share, right? Because everybody has proprietary stuff, but
Yeah, I'm presently working on patent for it, and as soon as I get that done, then I'll be glad to share with you guys everything.
okay, yeah. Well, in the meantime, if there are things that you're open to sharing, and again, stuff that's, and
Yeah.
I think a lot of folks have that, right? And that's
Yeah.
is
So I
when
can
you
go over,
have,
yeah, I can do some of the stuff that's not so proprietary that I can share because it's law common laws that I combine. So yeah, just send me the email or whatever so I can get with you guys because I have filmed that this meeting should take quite a while and I don't have time for all of it. Sorry.
oh, that's okay. That's okay. Well, Norman, thank you, sir. Thank you. And let
Yeah,
me,
thank
if it's okay, let me go to Ross next.
Okay, yes, thank you very much, you guys. Good luck. Thank you.
Hey,
Mr.
Sean.
Small.
Hey, so when I heard you say standing wave, it really reminded me of Milo Wolf's wave structure of matter, the WSM. Have you heard of that theory?
No, tell me about it.
Basically, like you had that wave that was, you call it a standing wave. That's exactly what he called it as well. And he even had a website. I think he's dead now, but he has a website called www.spaceandmotion.com, and it's in / Wolf wave structure matter.
Here, let me write it down.
Yeah, thank you for sharing that, Ross.
Or do you want to just put that in the chat for everybody?
Okay, I'll put the link in there right now in the chat. But yeah, you can see all of his visuals, his GIF images that he made. It looks exactly like yours with the
Oh yeah,
the standing wave. Yeah, that's his theory is of what the proton is. It's basically an in and out wave undulating, and it's basically a singularity, and then that's like, I guess, what we think of as an atom.
And you know what, Ross, let me do this if I can. There we go. I think this is what you're talking about, right? Solving nature's mystery.
Yeah, that guy right there, Milo
Yeah.
Wolf. Yep.
Yeah. So spaceandmotion.com, Wolf wave structure of matter.htm. And, even if you can't find the link, you can always Google that. And I will drop that in there as well.
It's just shockingly similar to your theories. It really is.
Yeah, I'll just scroll through. Wow, this is a big one. Woohoo, look at that.
Yeah, and there's multiple pages, and once you get into all the videos he's made of the standing waves, it's incredible. It looks just like your video of the undulating wave.
Lots of references too.
Yeah, and
So
even the
let
U.S.
me,
Navy actually created a standing wave. They had a wave pool where they had they did something with the waves on each end, and it was a huge water pool. I mean, like as big as a Olympic sized swimming pool. And there's a video on YouTube of them undulating these waves, and it's making these huge 20-foot standing waves that are just up and down, up and down. It's basically creates a standing wave. The U.S. Navy did this back in the 80s or 90s or whenever they did it. But even the Navy's been talking about standing waves for decades.
yeah. Well, Ross, if it's okay, let me go to Bill Alec. Bill has his hand up. Bill, go for it, sir.
Okay, can you hear me now?
Yeah,
Sean?
you sound great, sir. Oops, you lost your camera.
Ah. Am I back on?
Yeah, I can hear you. I don't see your camera though. Oh, you know what? Looks like, let me see. I'll do ask to start video.
Start video.
There we go.
Oh, okay. Yeah, Sean. Yeah, you mentioned subspace. Now, subspace came out of Star Trek. And Star Trek, back in the 60s, I'm not talking about the movies. The movies were lousy, okay, badly written. But the original Star Trek was channeled information from extraterrestrials. Believe it or not, these writers of Star Trek used to attend meetings in LA at this guy's house by the name of Jacques Dubier. Okay. He headed this organization called MIND, MIND. And these writers used to attend his sessions. And he channeled this information from ETs, and he spoke about all this fabulous technology, okay, that you saw in Star Trek. And I'm just wondering if this is somehow connected with instantaneous transmission through space using subspace as a means of transmission and reception of these type of signals.
Wait, Bill, let me jump in here. Where did you get this amazing history on Star Trek? Because I want to look this
I
up.
met the guy. He met before he passed away a number of years ago. Aurora was married to a channel, okay?
Okay.
And he used to channel these extraterrestrials. And we met with this guy in LA by the name of Jacques Dubier, and he was a channel as well. He was a fighter pilot in World War II, okay? And he had all these encounters with extraterrestrials, and they called them back then Foo Fighters, okay? And so his connections with these extraterrestrials, he started this organization in LA, and it was called MIND, M-I-N-D. And I used to have a videotape. You know, we videotaped this guy speaking about this. And Aurora, and back then her ex-husband, Michael, were very familiar with this guy. Okay.
I can't find him on Google, unfortunately.
Writers from Star Trek collected all this information, and that's what you saw on TV. I thought it was rather extraordinary. And one of them had to do with instantaneous communication using subspace. Okay. And you heard that kind of battered about in Star Trek here about using instantaneous communication using subspace communication. Okay. And I was just wondering if this is somehow connected with Sean's work here using subspace.
Well, yes, it can be used for communication. In this case, our three-dimensional space would be the subspace. I'm using the term subspace the way it's used in linear algebra. So you would think of our space is the subspace, and it exists inside of a higher dimensional, a space with more dimensions. And it's possible to reach up out of our space, as it were, and make stuff wiggle around and vibrate up in the hyperspace. And when you do that, you don't have to wait for the speed of light to get there.
Right. Right. Okay, so I think we have a future means of communication here. Very interesting. Okay, that's all that I have to say.
Bill, thank you, sir. So who should let's go to Jeremy G next.
Oh yes, I just have a question. It's about the subspace and the beyond. He sounds like faster than light travel. That's what you call quantum entanglement, right? It sounds like quantum entanglement.
Maybe. I mean, well, that area gets kind of messy.
I've never. Go ahead.
Go ahead. I'm sorry. Oh, it's like, say you send a signal out somewhere, and you're waiting for a bounce back, and then you record the bounce back. I know, like, how would you know what you hit the bounce back what if you would receive it or not? But say you did, and you took that signal, and I guess you took a previous recording of the signal you sent first, and then you have the information of the signal that you received back, and then you superimpose both of those signals, and then I guess you could maybe like fill out, like using turn that into a math equation as linear algebra or something, and then you could probably solve the distortion gaps by equalizing the equation. You know, the waveform, you turn the waveform frequency, you know, signal into a linear equation, you know, and then you solve for the missing you know, vector points or whichever, and then you actually clear the signal to become, you know, lossless. You know, there's no losses. So that's what I'm thinking you could do, and you get perfect communication, and that's how you would go faster than the speed of light, because you're getting rid of all the distortion in the signal, and thus I guess you have faster than light communication. Jeremy Reese talked about this when he mentioned the instanton, and that's like a mathematical formula or term describing this kind of thing with signal analysis, at least. So that's just my tidbit, and that sounds interesting.
All right.
Thank you, Jeremy. Let me see. Let me go to HK. Can I
Hi.
get you to turn your camera on, HK?
It's currently disabled. Take more time to enable it than not.
Okay.
Question I have is, you've built a transmitter. Have you built a receiver? And how are you modulating the signal? Is it a simple AM signal? Are you doing continuous wave? What kind of signal modulation have you put on it? And then what does the receiver look like?
Well, any antenna, can you guys hear me?
Yeah.
Any antenna,
Yeah.
any kind of antenna works equally well as for transmitting and receiving. So it's not like you need to build two separate antennas to transmit and receive. As far as modulation, I've tried pulses, which is, like I said, a very wide band spectrum of energy, and also a linear combination of frequencies. I guess that would kind of look like AM, the way you see the carrier and the two sidebands, only there's more and more sidebands. There's more than two sidebands. I mean, there's a lot. It's a good point you raised. There's a lot I have not tried. I mean, I have not tried FM, for example. There's a lot of possibilities.
Have you done a Faraday cage where you've built two antennas? You're transmitting one, the other one's inside the Faraday cage. So by having the cage, you're blocking everything imaginable. Have you done that and seen a signal?
That's a really good idea. I have operated the thing inside of a Faraday cage. It was inside of a shipping container made of steel. I did not have a second unit outside the thing. I had it in the Faraday cage just so I wouldn't create or receive interference. But
that would be experiment number one, to verify that you're transmitting and then you can receive, and then improving both the transmitter and receiving circuits.
That's a really good idea. Well, when I fired it up inside the Faraday cage, afterwards, as I was leaving, I had it in a shipping container at a marina, and I was walking away, and the harbor master came running up to me and grabbed me by the arm and started pointing at the sky. I looked up, and it was a cloudy day. There was a sheet of white cloud as far as you can see, except directly over the marina, there was this perfectly round circle of blue sky with sharp edges, like someone had just took a cookie cutter and cut out a slice of the clouds. I don't know if that was related to what I was doing or not, but it was certainly unusual.
Well, then the obvious thing is do it again and get a camera.
Right, I didn't have the presence of mind to take a picture.
Take notes, make a checklist. Here are experiments to do. there you've got a simple weather modification experiment. Do it.
Yeah, good idea. Good idea.
Okay, well, yeah, HK, thank you. Let me go to Robert Peterson next. I'm trying to work through these towards the top of the hour. When we get to 5, I'm thinking maybe I can get Andrew to share updates on the gravity cap work he's doing. Let me get Robert Peterson next. Robert? Sorry, Robert, you're super faint. Can you move your mic closer? I'm terribly sorry, sir. Give that a try. Yeah, it's still not working. Robert, why don't you work on that for a moment? Let me go to Aiden really quick.
Mike.
Oh, there we go. There we go. Okay.
Okay. Anyways, thank you. Yeah, I'm sort of new to this. It was very interesting, and what you mentioned, you sort of made this comment. Oh, this seems to be traveling instantaneous, so going faster than the speed of light. So what physical mechanism is this traveling through? It's not electromagnetic waves because they're limited to the speed of light.
It's
something big I'm missing here.
It's not traveling through our space. All we see is a 3-dimensional cross section of the wave. The wave exists in a space that has more dimensions than ours.
So we're working in a higher level dimension. Yeah. Then
John, what was your evidence for that? What did you observe, or how did you observe that? That the wave was more dimensions than we can observe.
Well, I don't know if I could really get into all that right now, but maybe we could talk in private about that.
Yeah, that might work.
I mean, it must have been observed somehow. I mean, other than the hole in the cloud.
Yeah,
Something
well,
must have led you on.
Sean, maybe you could, if it's okay, maybe you could drop your email into chat, and then Mike could email you, and you guys could kind of go through things there.
Sure.
Okay.
So I want to ask you, so are you saying that this is the electromagnetic waves actually have a higher dimension, and this is a higher dimension of electromagnetic waves, or is this some completely different process, or what?
I don't know if electromagnetic is the right word for it. It has to do with varying the Coulomb potential with respect to time. That's how you get at the stuff. But I think that there's a different force at work. There's something else that's at play besides anything to do with electromagnetism. But you can access that. You can push it on it, get it going by varying the Coulomb potential, by varying the charge on something.
Okay, actually, I'm being paged. I have to take it now. I'd like to, I don't know if I can talk to you a minute later, but
Okay.
thank you.
Well, Robert, thank you as well, sir. Thank you as well. And thank you to Mike. So if it's okay, let me see. It's 4:54. We're just about the top of the hour. If it's okay, I want to go to Drew to give us updates. And he was one of the folks, he emailed me beforehand. He wanted to give us updates on what he was doing. Drew, are you still here? Oops, let me find.
Yeah.
Well, work on hunter safety.
Okay. Yeah, Drew, do you want to do updates for us?
Sure. Before I forget though, who's the guy who said he talked to Elon Musk recently? Whoever it was, the new guy.
Let me see.
That Sean, or
you might have to look through. No,
anyhow,
it was.
I just curious because I have a tiny interest in maybe talking to him, but I know so many people that work for him, and they say he's the devil incarnate. So it scares me to death to even think about talking to him.
Well, and I guess one of the things to keep in mind is, you know, it could be that he sent a communication in but hasn't gotten a response back. It's always difficult to kind of tell. So,
All right. Well, if anybody's
yeah,
got
give us an update, sir.
a pathway to talking to Musk, I'd like to hear about it because I might be interested in that. All right. Let's see. Can I share screen
Yeah,
in this universe?
should be a green screen share button down at the bottom.
Yeah,
because we're in
so
Zoom.
looking for.
There we go. There we go.
Okay. All right. I just kind of pulled some random files. These are just random pictures. They're a little blurry, and I've kind of deleted some particular information because I don't know exactly how far into the physics I want to get. So, first we'll just go with the history. This is our little time chart. We kind of threw this into our presentation when we go talking to people, and you know, basically Charlie and I both started on this thing together about 2014. Charlie Bueller, and before that, I've got 10 years before that, and he's got about 12 years before that. But we worked independently and did all kinds of nonsense. It doesn't matter. By 2016, we were at about I don't know, 1/10,000th, 1/100,000th of unity, which is defined as the mass is the amount of thrust you make in, say, grams, divided by the mass of the thing trying to make the thrust in grams. So it's a unitless ratio. So by the time we got up to around 2019, we were about 1/10,000th of unity. By 2021, we were knocking on the door of about what is that? We're about 1/10,000th. Well into 22, we're up around 1/1000th of unity. Towards the end of 22, we were probably knocking on the door at 100th of unity. Then say 6 months ago, we were probably at around I don't know, 10% unity. And then as of 2 days ago, we are 1.17 times unity. So we can now make more thrust than the mass of the thruster to make the thrust. So yay for us. That's kind of the that's like not burying the lead. Let's see. Yeah, here's a super old picture, probably about 4 or 5 years ago now, of an early thruster. It made about 125 micronewtons. It spun that little wooden thing around, took about 3 minutes to make a full circle. We have videos of this. It's lots of fun. This is basically the thruster that Ivo knocked off of us. So, you know, this is what, just to give you an idea. And let's see. Close that. Here is the main slide I wanted to show. This is our, this is the just before Unity slide. So switch on the thruster, and this particular thruster is designed to charge continuously. It's like a super slow battery, kind of like a super capacitor. It just charges and charges and charges and charges. And the longer it charges, the more charge that's built up in it, the more thrust it'll actually make. So the only really interesting thing here is that we got all the way down to negative 3,500 micronewtons or 3.5 millinewtons, and the thing weighed 360 milligrams, basically. So if you do the math, it works out to 99.2% Earth to unity thrust to weight ratio. The other probably interesting piece of information off this thing is if you look at the current over here, this is the current line basically down here, and I'll save you the eye strain. It's basically 0.2 microamps, which works out to something like 1/4 of a milliamp per millinewton of thrust. But it's only important for the first one because you could stack 100 of these plates together and it would draw the same amount of current because this is a non-current device. It's an electrostatic device. So we're looking to, power our entire propulsion system off of the, the energy level in a cell phone. That's kind of important when you're, where you want to go. You don't want to drag thousands of pounds of batteries or stuff around with you. Let's see. This is kind of cool, but probably getting a quick peek at the test article. What you're looking at is looking into my vacuum chamber, my high vacuum chamber. All this mess here is just a simple load cell that has a full Gaussian shield around it, because every once in a while these things arc, and when they arc, they generate a pretty hellacious electromagnetic spike. And the electronics in here are fairly sensitive, so it shows up in as false data. So there's an ITO box wrapped around our test articles. What you're looking at is the actual thrust making plate. And it's kind of on a pendulum. It's attached. You can't see it, but there's a string right here that attaches this and right there. So it's just a very simple horizontal pendulum that generates the thrust. In this case, it's pulling backwards. So the thrust shows up as negative. And I'm pretty sure that's about it from the, yeah, I think that's about it.
Drew, thank you, sir. Thank you. Let me stop your share real quick, and let me see.
Sure.
I'll stop sharing. Yeah. Drew, that is an awesome update. Does anybody have questions here? I'll allow folks to unmute themselves. Oops. There we go. My camera didn't come back on for some reason. Okay. Yeah. So does anybody have questions for Drew on updates? Curtis is asking in chat. Let me see. Is it in vacuum? And if so, at what level?
Yeah, we're that test was run at about 3.5 times 10 to the minus 6. So it's hard vacuum from start to end.
That's amazing. That is amazing. Thank you so much for sharing that. Let me see. Shrish was asking what the velocity and momentum was. If you have that. Oh, sorry. Shrish Hala in chat was asking what the velocity and momentum you achieved was. And then Mark had a question too.
Well, the velocity would be 0. It's pulling against a load cell. The stroke on the load cell is like 0.2 millimeters. So it ain't going nowhere. And momentum, I don't know. I guess you could figure it out. Whatever. We made 3.5 millinewtons of thrust continuous against gravity because it's working. It's actually pulling down towards the Earth, but it's on an angle.
Well, there you go.
I don't know what to tell you.
No, that's awesome.
So Drew, I think sorry, I came on video myself, Tim. So I was just curious what you mean by thrust then, because my definition of thrust is very basic, very simple. Thrust produces a momentum. So that's when we show that something is translating through time, through space, etc. So how do you know that this can produce momentum and not just a force, which is stationary? That's really my basic question. Because you could have a closed system and bang it with like a massive actuators, and you could have a lot of thrust, but it would not produce any net momentum against the air, or so to say, right? So that's what that's why my question was.
I don't agree with anything you've actually said.
Why don't you agree with anything that I said?
Because I don't think any of it's right. When you are working against the Earth's gravity field, you're producing an acceleration. So what we're really doing is we're producing an acceleration that's showing up on that force meter.
Acceleration of what?
Well,
you got a propulsion system?
That's like
a
saying
propulsion system moves.
No.
Well, so again, he has the
he has the unit. Propulsion system produces thrust.
What is thrust? Define it.
Force. it produces force in whatever direction it's vectored in. That's like saying I put a rocket engine up against a mountain and fire the rocket engine. If the mountain doesn't move, I didn't make any thrust. That's an absurd
You
thought.
produced a force, not a momentum. There's
Who
a big
cares?
difference.
If you point the momentum toward the direction that you can generate motion in, you've made thrust. In this case, we're working against gravity, if you will.
Doesn't matter. You should still have some movement.
No. Why would you have movement? You're working, you're pulling against the load cell. The load cell isn't allowing any motion. It's recording, it's literally eating all of the energy you're putting into it and giving you an electronic signal out.
Yeah, that just measures force.
What more do you want to measure?
You want to measure that it is translating against, you said you have thrust per unit mass, etc., right? When you say something is moving, you got to show that it is moving, right?
No, you don't got to show that it's moving. I already said I don't believe in anything you just said.
And neither do I, because
Okay.
you're not making any sense. Anything
Okay,
can
well,
produce thrust then,
One of us has an engine and the other is asking questions about it. Take of that what you will.
What engine do you have? If it doesn't move anything, then how do you call it? You could just put you could just put an actuator against a wall and say that it produces thrust. That doesn't mean anything. It's not going to move the vehicle.
What did the actuator
Anyway,
push
that's fine.
against
That's
in order
fine.
to make this?
You know what?
Okay.
You're doing whatever you are. I mean, I asked you a serious question, but by just taking digs at me on
And I
this, I
answered
mean,
it.
I
You
asked a
just didn't
simple
like the
basic
answer.
question. Okay. And if you don't want to answer
And I
that, I'm not
answered it, and
asking
you
you
didn't
to.
like the
Yeah.
Don't
answer.
bother.
Well, guys, yeah. Why don't we move on? Let's move on to Mark, and then the impression that I get is it's more of a communications issue, but yeah, let's
Jim,
move on to
if
Mark.
you have a propulsion system, propulsion things move things. They don't stand still. It's a simple thing.
Actually, rocket engines on test stands stand very still. And they
any
Yes, because they're
propulsion
measuring
system
thrust, but they also produce momentum, and that's my simple question was that, what is the momentum you're getting?
Move on the test stand, and if it
Yeah,
does,
but they don't stay there forever.
You won't have. No, yeah, I'm sorry. I agree with Drew and I agree with Mark.
I'm sorry,
you won't
guys.
if it's constrained.
I
If
actually
the
build
motion is
rocket
constrained, you
engine
won't have
stands
any.
for a living. Okay.
Yes.
I literally, I'm a rocket engineer. I literally build rocket test stands for a living. I have a little bit of understanding in this field, considering I've been in it for 35 years. I know everything there is to know about rocket engines. I'm telling you, this is a propulsion system. It just isn't a chemical propulsion system.
Well, first of all, I think there's a round of applause, Drew, on getting past Unity. That is really big.
Yeah, Drew,
that is really big.
Yeah, that is amazing. Yeah,
this is truly amazing. And you've been at this for what, like almost 10 years now?
19.
Well, since 2014, that's what I was going off. Okay, 19 years.
I teamed up with Charlie in 2014.
Yeah, and before that, you had some other people that you were working with as well.
Okay.
Like you just mentioned, also launched in the last 3 hours. They're on Transporter 9. They are in low Earth orbit right now, and maybe we'll hear something from them soon. I think, Drew, you said that their device is similar to yours, and you think it'll work?
It's a knockoff of our earliest version when we patented. Our international patent crashed, and they basically took our international patent and built something, and then claimed it was theirs. But yeah,
that's the IVO system, right? Just to
the IVO system launched 3 hours ago. So
I don't think they're going to release from the from whatever thing took them up there. I don't think they release for a couple of days, if not a couple of weeks. I kind of read the weird release cycle.
There's a lot of satellites on that thing. I was actually looking at that right now. And there's several hundred, 113 payloads are on that thing. So there's gonna be a sequence in which way they get removed. So right now it's in orbit, probably hasn't even been released yet, but that's really amazing news.
It's probably gonna be 2 to 3 weeks before they're released. And as I understand it, they only got like 40 millinewtons of thrust, and their thing weighs, I don't know, 150 pounds. So
No, it can't weigh 150 pounds. Not for.
Oh yeah, I personally think they're tied directly to the launcher. I think they're actually integrated into the giant launcher machine. It's kind of like a sub kernel of the big payload discharger thing. I think they're actually tied into the payload discharger thing. So they're probably part of a very large structure. And that's my guess as to, that's my guess as to what they're doing. I really don't know. I don't talk to them. My attorney does.
Oh, Rick is asking what's moving in Drew's device to yield thrust.
Space.
Excuse me?
Yes. Space time.
What's moving?
That would be the
Oh,
idea.
nothing is actually moving. My best guess on that is I showed this a couple of weeks ago. Is all them little things that wink in and out, wink in and wink out of subspace, whatever you want to call them, the little Planck
Virtual
scale
particles.
virtual. Thank you. I don't know quantum mechanics. Virtual particles winking in and winking out. They're slamming up against real charge. Boom. When they slam up against real charge, they transfer momentum, then they wink out. That summation of transferred momentum from virtual particles is what I think we're draining from, and I call it subspace because I love Star Trek. So I think we're actually sucking momentum directly out of subspace. And at some point in life, I'm sure God's going to send me a bill and, we'll ignore it. But until then, we're just going to take our free momentum from subspace because it sure ain't the power we're putting in. These are microwatts. It's just literally microwatts to generate the thrust. That ain't where the energy's coming from.
What was the subspace again?
The question that I had was for you, Drew, is the over Unity. How much is the weight of the test sample, and does that include power supply or battery?
No. Just this is no. This is literally just the test article, just a little piece of plastic that's doing all the work. It doesn't mean the frame, and it doesn't mean the power supply and the vacuum chamber around it, because all that stuff is going to come and it's going to go as the design changes. This is the core material. If you took a little piece of this plastic,
that's still big.
right? If you took a little piece of this plastic and set it on a scale and applied the energy to it, it would have at some point it would lift up. It would actually there's no control system into it, but it would be a nightmare. Essentially, we are generating, because the thing weighs 365 milligrams or 360 milligrams, and we're generating more than 360 milligrams of continuous acceleration force.
Right.
The math is simple. When you make more than you weigh, you will have achieved unity plus.
Also, have you seen the Lafroig thruster?
LaForge.
LaForge, yeah. It's actually almost the exact same thing that you have in your patent.
No, I haven't.
Check it out. It's in the chat. There's Rod Chambers put the link in. That's something actually me and Jeremiah built.
Subspace.
That's something that me and Jeremiah built a while ago.
I think I remember you building that, Mark. Yeah. And I experimented with that too. The one I used was the gravity capacitor, which I think is just another name for the LaForge thruster. And I think the version I built came from Nadan's site also.
Yeah, I spent a lot of time on this guy's site 20 years ago.
Yeah.
So which one is it? There's a lot of them on this site. This is their little yes. Do you know why their LaForge FP thruster works? Because it's asymmetrical pressure.
Mine is different. I built a traditional gravity cap, but yeah, I've looked at the LaForge one many times. So
yeah, because it's asymmetric in its surface area.
It's basically an asymmetrical capacitor. Yes. Yeah. The only difference between that one and ours is that's using a volumetric asymmetry. So it achieves the asymmetry of the field by a volume shape. In other words, the shapes of the things on the sides, the shape of the little mountain in the middle, whatever you want to call the thing, the horseshoe shape thing. We do not do that anymore. We have evolved past physical shape asymmetry and gone a whole nother route. which has allowed us to cut the weight down by, I don't know, factor of 10,000. It's very cool.
Great job, Drew. Congratulations.
Thank you.
Okay. So let me go. I guess I can go back to HK. HK is his hand raised, and then we go to Robert Peterson after that.
Drew, congratulations. And have you run the calculation of thrust out per joule of energy in?
Yeah, it makes no sense.
Sure. I mean,
Again, our
one
joules
joule.
are virtually zero.
So
I'm sorry, go ahead.
What's your conversion rate? So, I mean, a joule, 1 Newton of thrust is defined as 1 joule. So what I'm curious as to how much thrust are you getting out per joule of input?
Okay, I haven't done that math, but I have done watts. And it's something I did it this morning. It's something ridiculous like 0.3 milliwatts per millinewton.
Okay.
0.3 microwatts, 0.3 milliwatts, probably 0.3 milliwatts.
Okay.
But that's not important because I could also run 100 more of these plates on that same amount of power. So it's just because that's the math for this one plate doesn't mean anything. Again, this is an electrostatic engine. You can run 1,000 of these plates on the same voltage power supply, and it'll still draw the same amount of current. The current is what it takes to run the power supply, not to run the propulsion system. That's why it doesn't make any sense when you look at energy in, energy out. We're getting free. Some this is an over unity, free energy, free propulsion thing from the universe. Yes, it is. Yes, it is.
So the way it's really working is it's extending the electrostatic field, and because the area of the electrostatic field, it keeps on getting bigger by stacking more of these units, you're getting more thrust.
Like creating more poles.
Sure. Yeah, you're just creating more places to trap the little. It's kind of like I'm putting up a sail, and you put up a sail that's whatever the size of a small sailboat, and whatever wind. Let's say you're putting up a sail in a continuous wind. If you put up a sail, boom, you're going to start capturing momentum from the air.
Right, you're creating more surface area.
Right, it doesn't cost you any more energy to put up a four-size.
More poles on the surface.
The energy is coming from the universe. Literally, I'm the first to tell you this shouldn't work. The only way this works is if you're stealing energy from God, which we are, or the universe, whatever. We're stealing energy out of the universe.
How quickly can you kill the electrostatic field? So in the sense, the reason I'm asking is then because you want to do directionality, light up different units.
That. When we're talking about the version, there's two versions of our thrusters right now. We just call it the quick and we call it the fast and the slow version. The fast version, you turn them off and it goes to zero in I don't know, 15 seconds, 20 seconds. You're at zero. The slow version, once that puppy's charged, it's a real bear to get that charge out of there. It discharges at about the same rate that it charges, and it charges real slow.
But Drew, if I could jump in, essentially this is a capacitor, so you could design discharge circuits for it, right? So that would be a piece of cake.
This is really not a capacitor so much as that it's a
dielectric. It's an insulator that can be polarized.
It's a dielectric supercapacitor, and they're not so easy to discharge when it's a dielectric.
I get what you're saying.
Because they can be polarized, and the longer you're polarizing, the more you saturate.
Yeah.
More poles on
the more
more little poles.
The more charge you pack into this puppy. And by the way, this is all in our new patent.
North poles.
Patent release should be out. I don't know, sometime. It should be out already. The more charge you pack into this puppy, the more it can trap momentum from what I'm going to call subspace, because again, I love Star Trek. So more charge equals more thrust, or more surface area equals more thrust. More surface area plus more charge equals lots more thrust.
So it sounds like
why
the
it
way
took
to
10,000
Being an insulator,
seconds
you
to
don't
charge
use
the
power.
thing. Right, it's basically it's the energy required to generate the electrostatic field, which is we got a pretty good little power supply.
Yeah,
You know, it's
and if I
a little
could,
Spellman power supply.
if I could
Wimhurst generator?
suggest, if I could suggest, for folks wanting to learn a little bit more, this isn't a 1-for-1, but I would probably look up the Casimir effect, which seems like it is similar in some
It
ways.
is. It's exactly.
I'd say the Wimhurst generator is more along the lines.
No, it wouldn't be a Wim. It wouldn't be a
what?
Wimshurst. The physics behind
No,
It's like
it's
a
definitely
static
a Casimir
building
effect.
device.
Yeah, but Mike, you're kind of missing the point. The point is that if he's tapping the energy of virtual particles, it would be like the Casimir effect, which
Is this similar to like quantum locking with like nitrogen over a magnet? No, it's totally
No.
different.
Yeah,
Okay.
that's different.
Yeah.
That's just trapping magnetic force lines. So the Casimir effect, basically you take two plates, they're not charged. You take two plates, you put them very, very, very close together, and they will generate a force. And the reason is because that vacuum energy, the distance between those plates, as well as the size of them, the geometry, it blocks out natural wavelengths in the quantum vacuum energy. That's the idea behind it. And so literally by just having two non-charged plates sitting right next to each other, the universe is generating all of these potential standing waveforms, and it can't generate standing waveforms between those of certain frequencies, so it creates a pressure. So what Drew is talking about is similar to that, except directional. That's the idea.
It's cool.
And to expound on what Tim just said, those plates aren't going anywhere, and yet they're measuring force on them. How is that possible? Because you can measure force on things that don't move.
Well, you increase the charge in between the layers, they're going to want to,
No. A Casimir effect sensor doesn't have, the charge is exactly the same. They're tied together. They're literally tied together. You're just measuring the force on the individual plates. And as you shrink the gap, like Tim said, you're changing what parts of the universe, the little wink ins and wink outs, can get in there to do the work.
Smaller and smaller frequencies can get in.
The resonant cavity is preventing longer wavelengths from occurring. So on the outside of the plates, you have pressure going in there, and you don't have a balance anymore when they're close together. So you have excluded frequencies between the plates, which means that the outside forces are greater, and you are able to overcome the
difference.
lesser.
The difference being that Drew is polarizing the charge on his, and he has some secret sauce going on as well.
We figured out a way to amplify the asymmetry of the Casimir effect. We literally can dial up turn the knob and generate as much Casimir momentum stealing as we want in a vector direction.
Well, if it's okay, let me go to Mike really quick, and then I'll go to Curtis.
Drew, how did you describe is there some simple way you would describe subspace?
I have no idea what subspace looks like. In my vision, I look at a Planck scale, like a little lava bubbling, blah, 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 things winking in and winking out in 3 dimensions. Other than that, I have no clue what's going on.
I'm not a physicist.
What about regular space? How
look at the generations of matter. So generations of matter, that's the energy content, the difference between the muon and the lepton and the energy density. So there's three levels to subspace, and we're ignoring them. That energy is coming from somewhere. So,
and we see regular space as the horizontal and the vertical, and that's it, and the depth.
Well, okay. So what Drew kind of alluded to is quantum foam, right? And I dropped a link in there to quantum foam. The idea behind quantum foam is, so normal space, this is the idea at least, normal space is empty. But one of the proposed ideas, I think this is Hal Puthoff, as well as several others have been working on this, is that normal space has particles, electrons, protons, you name it, that pop in and out of existence, but they do so rapidly. They're virtual particles. They do so rapidly that they don't truly exist. However, they do exist for just fractions of a split second, which potentially creates inertia, potentially creates gravity. And so it's this idea between the interaction between matter, which exists all the time, right? Electrons and protons, and these virtual particles that again appear and disappear so rapidly that you can't even measure them. And that flux of these particles appearing and disappearing, as well as these minute fields, are what they call the quantum foam.
The subspace.
And subspace isn't and subspace is not, that's just kind of a Star Trek term, right? That's what we're calling it.
I know, but that's a good description. Quantum foam is a good analogy.
Sure.
For it.
But then
it's also the quark body. It's the same sort of dance is going on within the quark body. When we're taught quantum chromodynamics, everybody just stops at the valence quarks, but there's this body of quarks that are doing this shifting. PBS just covered this, and they said they got into there's this charmonium pair that is briefly within the quark body, and this little pair, charm anti-charm pair, has more mass and energy than the rest of the proton for a brief second. So the subspace, it's all covered. We're not looking at the second and third generation of matter. That's where this energy is coming from and going back to.
Yeah, and I can't speak to any of that, Aiden, but thank you. Folks Aiden, do you have a link that you might be able to drop in that people could look that up?
Yeah. It was PBS Space and Time did a real good discussion of it. It was a breakthrough.
Second generation of matter.
But yeah, up, down, strange charm, top, bottom, quarks, first, second, and third, and then down. Below. This is all straight down. Standard model. Electron, muon, tauon. So just we're stopping at up and down quarks and the electron. We're ignoring the charm and strange and then top and bottom. So that's where we got to go for learning where energy is and real energy density. I'm sticking with the standard model, Tim, but let me get the link and I'll throw it in.
Thank you.
I basically see it as a shape that's kind of like not meant to exist in our 3D space, like the Gumbach, and it can't find equilibrium when it's like they made a shape by 3D printing, and it can't find equilibrium. When it's going back and forth, it constantly moves, and it doesn't ever seem to stop going left to right. So I don't know if that has something to do with repulsing forces based on the shape, but I see the virtual particles or the signals that you can't detect. I see it in a topological matrix kind. So you say you have the waveform, you got the waveform, and you get the nodes and antinodes, and then you put them on their plot points to where they are, on a X and Y, I guess, grid, and it's 3D space at least, and then you would then draw a shape out of that, and that's kind of like I would use that as it's the equivalent to the signal you got. It shows you the shape of the signal, and that what I think would be the hyperdimensional map of how fast the particles are going. That's the wave motion mechanics that all the particles are doing. You actually get the shape in a 3D space. So that's all the motion going on. The shape that you get out of the signal. That's all the motion. So that's what I'm thinking.
Well, Jeremy, thank you. Let me, if it's okay, let me go to Curtis. I'm just trying to move things along because we're starting to pile up hands here.
No, I actually had a question. Jeremy, did you get a chance to see my presentation at the last APEC?
Oops.
I don't, but I'll have to watch it.
I'm just kind of curious if you guys got to see that.
No, but Curtis, you do have an update today. But
That's
let me,
what-
you know what,
okay.
Robert Peterson had a question too. So
Sure. Well, Drew, have you seen that? Oh, sorry, go ahead.
All right. Yeah, calling
Is that
me.
question for me?
Do I go on now or?
Sorry.
Are you waiting for me now? Okay, I guess podium is for me, I guess.
Yeah.
Yeah. Further getting, I'm really intrigued. I know about this possibility of communicating faster than the speed of light. I thought that was such a, an absolute limit, and I'm still trying to get more of a sense of the nature of this. Is this something outside of electromagnetics, or someone was mentioning higher order?
Quantum entanglement.
Oh,
Two
so this is
electrons.
quantum entanglement. Now, has this actually been observed or anything, or is this a sort of a hypothesis?
So Robert, I could probably speak to that a bit in terms of standard quantum entanglement. That's very well, that's very well demonstrated and observed. If you look that up, now there are some limitations there. There's something called
Doesn't
no
the double
communication.
slit experiment demonstrate that? No?
So there's something called the no communication theorem, which claims that you can't communicate faster than light using quantum entanglement. And the idea behind that is actually that the measurements of it that you would use for the communication part have to basically travel within the speed of light. So you're still stuck, right? But there may be workarounds for that. And I actually did an interview with a founder of the John Bell Institute. John Bell was the physicist who came up with the no communication theorem, as I recall. And a fellow named Dr. Tim Maudlin from New York University. And he believes there are several workarounds that would allow that. So that's just on the quantum level. There may be other levels as well, right? So the idea behind string theory, string is one of several different approaches to kind of like a multi-manifold theory. And you could almost look at that like, so in Robert Heinlein's Stranger in a Strange Land, right? That goes back to this whole flatland discussion of you have planes of existence, you have dimensions of existence. And in the case, like in Stranger in a Strange Land, he learned how to flip things so that it was facing perpendicular to all of the dimensions, right? So this would be like looking at something edge on in flatland. It just disappears. The idea behind that is similar to basically a higher dimensional manifold. There have been approaches to this, like Kaluza-Klein was an early one. Einstein's unified field theory used he used torsion to connect gravity, and the other one he was basically saying spin is kind of another dimension. So the word dimension, Todd and I have had some disagreements about this. I try and use the word manifold now because I think it expresses it a little better. But so yeah, there are a lot of different approaches to it, but at present, I'm not sure if any have been demonstrated, right?
Now, with this device, you hypothesized that this was basically entering one of these modes, or was there the feeling that this device was, entering one of these different modes involving entanglement or something else? Not limited.
Well, an orthogonal field, when you invert it, you have two ice cream cones coming together. That shape right there, when you hold it at any angle, it pretty much produces all the shapes that you know. And when you charge something like a dielectric, it's pretty possible that there's plenty of orthogonal fields being generated. Just to throw that out there.
Yeah. Well,
yeah, go ahead. Yep.
Oh, I'm sorry. Well, Robert, why don't you finish and then I'll go to Curtis, because Curtis had some updates on his.
Just commenting that this is opening whole new dimensions to me, so I'm interested in what this man was explaining. And if you could maybe throw out a few bits that are easy to grab onto that I could then Google on or look up.
there's so many speculative approaches to this. This is just my opinion, right? I could be easily mistaken, but I look at the speed of light as kind of a wave velocity, right? Almost like the speed of sound. I look at that as the wave propagation velocity through the vacuum. And that would explain why gravity and everything else tends to follow that, right? But it doesn't mean, I mean, like they have was it the shortest distance between 2 points, then they fold the paper over and poke the pencil through it. I think that that's entirely valid. Just whether or not we can do it yet is another question, right?
I think math would be a big help for that, and I think we can use regular equipment that we have to actually probably achieve that. I think it's very possible.
I think the math
research Ralph
for
Ring.
So I would look at ER equals EPR. That's something that Jack Sarfati has been really excited about. That comes out of the work of Leonard Susskind and Juan Maldacena, and more or less, in some ways, they're saying that wormholes are the same thing as black holes. Sorry. Wormholes are the same thing as entanglement. That's the idea behind it.
Yes, there was a paper by NASA that I had found. I had to dig it up again, but they used a small wavelength supposedly to stabilize a black hole or something. It was I don't know if it was a simulation, but yet they said they might have done it. I have to dig it up again. So that's all I'm going to elaborate on that.
As a simulation, yeah.
Yes.
Well, if it's okay, let me go to Curtis, guys. Curtis,
so
did you?
So the quick thing to bite on here, you're saying there's this paper by NASA. Just throw out one thing for me to get started on here. So I'd look for this paper by NASA, or was there something else I should just do a quick bite on?
I would look up quantum communication. That's where I would start.
That sounds interesting.
Yeah.
Okay.
Well, the thing about the two electrons, one's spinning clockwise, the other's spinning counterclockwise. So when the one on Earth is spinning, and they change direction they spin based on, if you spin the one on Earth clockwise and then you change its spin changes on the other location, the one on Earth should change its spin also at the same time. And by doing that, they can convert spin changes into a binary language and then have communication.
Yeah,
every time the spin changes, it's like a on and or an off,
Okay, well, why don't we go to Curtis now? And Curtis, do you have a presentation? Do you have an update for us?
Yeah, I have a couple things to talk about. Actually, I wanted to jump in the conversation. First of all, you guys are talking about something that I don't know if Drew saw my presentation last time, a couple weeks back. Did you get a chance to see that, Drew?
Oh, sorry. I have.
Can you just refresh what it is?
Yeah, just go over it, Curtis.
Yeah. So let me share my screen and I'll go over. Let's see. There we go. Okay, you guys can see my desktop. So this was one of the slides I had last time. Can you guys see that okay?
Yeah. Yep.
Okay.
It looks great.
So the theory I covered last time, I don't know if you guys all saw it, but basically it's a quaternion based formulation of general relativity that breaks up the symmetry, and kind of like what Dirac did with the Klein-Gordon equation, and you actually get more information, right? You get more equations out of it. One of the consequences is of doing that, you end up with a prediction for particle-antiparticle pairs when they come together, that the pair actually couples electromagnetically, but the gravity field still exists. So in this theory, there's not a conversion from electrical energy to mass inertia. Basically, the electrical energy field of the matter you get an electron and a positron close enough together, they're tightly coupled in a ground state that happens to require the same amount of energy that, 2mc squared. Okay, so there's a couple consequences of that. One is that could be the mechanism for the Mach effect, where we notice that inertial mass seems to have a thing where there's no momentum, and you can look at the distant stars. If you rotate something, right, it behaves differently. And the other thing is, that background pair gas has to do with the speed of light, right? That was, the discussion that we were having here. If you remember when I was describing this background pair gas, potential background pair gas, if you reduce the density of that background pair gas, right? If you think of the ocean, right? And you're sending signals through waves of the ocean, right? You have a certain wave speed. You can't violate that, right? But if you lowered the level of the ocean where there's no water anymore, and you can take a jet or just, go much faster, right? And you have a bucket of water that you're just transporting, that doesn't violate the wave equation, right? That doesn't violate any physics. So if this theory is correct, and there is a background pair gas that we're in, and you lower that background pair density, then you can, in anything in that volume, you can do that for potentially like having a shell where you're using the Brightwiller mechanism or nonlinear Brightwiller process and splitting up background pairs. And so that in a volume, you have a reduction of that density. You can, you have a much less mass. Now, one of the other things about this theory is that it doesn't ignore the problems with the Mach effect just by itself, in terms of just having to do with inertia. In this theory, not only mass, but charge and magnetic moment are also coupled to that density of the background pairs. So it's called, in the theory, Mendel-Sachs calls it the generalized Mach principle. So anyway, so the second relevant to propulsion a consequence of this theory is that the background pair gas, you could take that, split up the pairs, and if you throw them both in the same direction, you could actually produce a thrust, right? Because you're taking a electron positron, breaking it up, and you can turn the positron around, send and with the magnetic field and an electric field, throw the electron one way, and then have a different area where there's opposite electric field throwing the positron the other way, right? So if this theory is correct, you could take background pairs and you can throw them in one direction. Of course, if you're already reducing inertial mass, you're already using a lot of energy and some kind of skin, and splitting them up, you might as well direct them one way, the opposite of where you want to go, right? So that's what I covered last time, and that I found that very relevant to the discussion you guys were having, because potentially, I mean, if Sachs is right about how things are, potentially the device that Drew has made, it could be doing this type of process where he's splitting up pairs and getting a preferential flow in one direction versus another. I don't know, but I thought I'd throw that in there. Okay, so Drew, did that I don't know if you saw my talk last week. Do you have any comments on that?
No, I would have to watch it. I've been busy with other work.
Sure.
I mean, high voltage would split pairs. I don't see why not.
Yeah, it takes a lot of energy.
Or high potential, not necessarily high wattage, but high potential. Maybe
I love the potentials. I try to move away
high
from
voltage.
magnetic, magnetic field, magnetic vectors or electric vectors. I try to move away from that and just do, like I said, with Coulombs or just potentials in general. as a measurement. Sorry, go ahead.
I believe once you start having magnetic, you're dealing with you're having current showing up now, not just voltage. Once you have magnet, any type of magnetism, I guess iron will help create your current from that voltage.
Yes.
So right now,
show up in magnetism.
The standard way of producing particle antiparticles. I mean, you could do this in the physics lab. You just have some gamma rays, gamma ray energy. So it's really high energy. They have to collide, come together, and you get a positron and electron produced. There's also something called the nonlinear Brett-Wheeler process, where you would have you could have like a field, a laser field, pretty high energy laser field. It's also called the multi-photon Brett-Wheeler process. So you'd have one gamma ray in this laser field, and you could split up a pair. So there is a kind of precedence for nonlinear, or kind of maybe in matter, or maybe there's like a nonlinear way, or less energetic way, I would say, in terms of like overall energetic. You still need the energy, right? You still need to break up the pair, but some kind of intelligent material, or intelligently constructed material that like preferentially breaks up the pairs and then sends them in the right direction. So in this theory, that's possible. And one of the slides I just wanted to show it. One of the slides that kind of goofed up was last time was this one here. There's not that much, where I had showed a first order vector and a spinor quaternion. That kind of goofed up last time, and I think that slide I was showing where I had this text here and the equations. Also, I didn't cover the references. There is a paper on arXiv that goes over Mendel-Sachs's equations and does a short-sighted solution, a very detailed derivation of that. It's a good paper, but it focuses basically on general relativity. The questions I got afterwards, people contacted me via LinkedIn and other places. One question was wanting me to go over. Here, I'll do this one first. This is the most relevant one. Basically, this is a Mendel-Sachs book, General Relativity and Matter. And I just wanted to go over the section where he covers and where he does do the derivation of the mass of an electron and a muon. So in the theory, if you guys saw my presentation last time, basically it's a quaternion theory, and it's a field theory, a strict field theory. So there are no infinities. Everything is standard mathematics. But you are using spinors and or quaternions in addition to tensors. Okay, so in this theory, basically Sachs, using the field equations, he ends up. I'll just move ahead with that because I don't want to go over that derivation. But he ends up coming up with a mass doublet, which is what we observe in nature, right? You get an electron and you get a muon that's like 206 times the mass of the electron, and there are mass doublets are observed. So that comes out of the theory. And what Sachs does is he basically figures out a way to calculate if he postulates that, okay, the inertial mass that we measure is from the generalized Mach effect is the interaction of that electron with the background pair gas that's around it. So he ends up deriving a density relation to the mass. You can see that right here. And in my talk I said like directly related to, but it's really like you can see here it's in his derivation it's to the 1/3 power. And so what he does, and I'll kind of skip over some of this. I mean, here he's looking at like energy states and like showing that there's what that ratio is for the mass doublet. So that's 206 times. And in addition, he postulates that the density should be He just kind of takes a guess using Avogadro's number of pairs in a molar volume. So basically, he comes up with the density using that argument. And putting that back into the equation, this is what he gets for he gets the correct mass for the electron. And of course, if you take that multiplied by 206, you get the muon mass. So that's where that's actually one of the only theories that I've seen that actually calculates from first principles the mass of matter and gives a reason why using Mach's principle here. So anyway, so if you guys want to see more of that, or if you have questions for me about the theory or anything you want to see in detail, like I said, I'm only covering this section here of that derivation because I got asked that question.
Is the doublet the same thing as like a Cooper pair?
No,
You know,
it's if you recall, somebody was mentioning the standard model where there's a electron muon.
That's me.
Yeah, that's yeah. Okay. Yeah, so basically it's the doublet, the mass doublet is like the electron and the muon in the standard model. So the tauon is not predicted in that theory, and it could be
going a little bit better here.
I'm sorry, what was that?
No, that was sound like Mark for a moment.
Okay.
The tauon's not predicted, you were saying.
Yeah, but he does cover pions, and of course the proton. The neutron is a combination of the electron and a proton.
Plus the neutrino.
The neutrino in this theory is comes out of the electromagnetic portion of the theory. So in Sachs's theory, I don't know if you saw my talk last week, but basically you end up with the quaternion theory, you end up with getting E and M, but getting some extra predictions. So I can, what I might do is
yeah, your presentation woke me up and it was very exciting. It's sometimes these, I don't want to be rude, but it piqued my curiosity and held my attention. So yeah, I appreciate your presentation from the last one.
Oh, that's great. Thank you. Yeah, like I said last time, if you guys have any questions or if anyone wants to, collaborate with anything, let me know. I'm looking for collaborators, and like I said, I'm trying to figure out. I did some work, and there are some libraries in Python like SymPy that can do symbolic stuff. And so I'm looking to put a open source kind of like GitHub repository that people can go in and fork or just contribute to. I think it would be fun to like put all his theory up there and like put it in a form where people could actually use it and do computations like really easily.
It sounds like something that physics GPT. Sorry, I don't want to damn it, but if we could have that shuffled over to Jonathan and Jeremy and our physics AI.
Oh yeah, that'd be great. I've been looking for at pins. They're called pins, physics informed neural networks, and I heard of there's a AI Feynman. There was a project someone was doing where they trained AI to replicate like a few hundred different equations that Feynman had derived, and you can like go in there, give it data, give it the parameters, and it'll like predict an equation. So someone used it. They put in the data Kepler had and the parameters he's looking for, and it took it 4 hours to figure out Kepler's law. So that's pretty impressive. It took Kepler, I think, 4 weeks or 4 years. How long was it?
A while. He was up. He was doing calculations by night at night, and it was years that he was working on his laws. So I'm tickling an old astronomy memory.
It was something like that. It was, but the AI wins, right? That's the thing we're all worried about.
It only wins if we let it win, or
for computation it wins.
Yes.
I would be hesitant on relying on ChatGPT for computation, though. I've read that it is not that good with math.
It's not. Well, it needs, like, you can actually do the plugin with Wolfram, so it'll go ask Wolfram. And so, you know, with Python, there's Python libraries that are really good, right? They're used for good things. So, and in case anyone missed last time, so I just real quick. So basically, what Sachs did, you know, the heart of it is that he took Einstein's field equations, he factorized it, just like Dirac had done with the Klein-Gordon. And you get these field equations that if you combine them, you can recover Einstein field equation in one way, where you take the positive symmetric tensor fields. And if you take the anti-symmetric version, the one with the minuses here, you can recover a set of 6 equations which map to Maxwell's field equations. And I've since I gave that talk, I've been looking, and I've seen that there's people that have, you know, made electromagnetic or electromagnetism quaternion versions, and also using Clifford algebras and stuff like that. So it's all basically the same thing as this, what we have here. So yeah, I think you know, this gives, the thing I like about this is that it's based on just a few physics like assumptions, which is, okay, Einstein was right about covariance. Einstein was right about Mach's principle, but we have to generalize it, right? Because we know that charge, if charge stays the same and mass changes, that's a problem, right? We don't observe that. So, but with those basic principles, you can, you know, and knowing that the matter is a wave, right? It's a wave on top of the, you know, we're waves on top of that dense ocean. Knowing that about ourselves, now the speed of light makes sense. All these things kind of pop out, but it gives us a path forward to, like, okay, well, if we want propulsion, what can we do, right? We can take that then C and like split it up and shoot it one direction, right? So at least it gives us a chance that it is not based on you know, a speculative idea. These are good physical principles underlie this theory.
Okay, so on that propellantless propulsion, you're saying you're actually shooting the whatever the C stuff is backwards so that you go forwards? It's just a mass.
Yeah, so basically the Brett-Wheeler process breaks up an electron and positron pair. And what I propose here, and this is something that, you know, can be done, like you could do this in a lab. If you break up a positron electron, if you have an electric field, let's say it's pointing this way, the electron will move that direction. Well, a positron will go the opposite way. And on that side, if you put a magnetic field, you can actually turn the electron, right? I mean, the positron, right? So any charge going through a magnetic field will experience that curve, right? We all know that it curves around. And so that can be curved around to another volume where you have the opposite electric field. And so the positron will also go that way. So it's just like you know, this maybe the stuff you're doing, I don't know, but maybe at the micro level, it might be doing something similar to this. Maybe the stuff that we're doing in the lab at Fullerton with the Mach effect, maybe it's doing something like this inside the cavities of the piezoelectric. I don't really know. I don't have any evidence one way or another, but I'm just saying that this theory is like showing an explicit mechanism for the Mach principle that gives us, if it's correct, that gives us a potential like mechanism to do these things that we're trying to do.
I figured that mass is a wave as well. It's a frequency actually. If you use the general equation, it's just a frequency that leads to a chronon. Have you heard of a chronon?
Yes.
Yeah. So for me, that's a building block. So I'm pretty surprised you come from a completely different angle to figure the same thing.
Yeah, so, I mean, it's like I said, it's kind of the reason I even thought of giving this talk, one, I'm working with Jim, but one thing I realized is I saw these recently, all this UAP, you know, UFO talk, and it kind of just reminded me that, oh yeah, well, you know, there's that physics theory that actually completes general relativity, makes it compatible with what we observe in quantum mechanics, and actually is quantum mechanics comes out of it as a linear approximation. So it's completely compatible with everything we observe on that side. And on top of that, you know, if this is right, if there's a background pair of gas throughout the universe, we are observing that in, you know, with what Hubble is seeing and what James Webb has seen. It just it kind of seems to me that, okay, there might be, you know, there's a plausible thing here. And what I like about this too is that it's a thing you can experiment. So what Sachs says is that there's a countable number of pairs in the volume. So in quantum theory, it's okay. The volume is, you can get infinite energy. With this theory, it's not like that. So there's some differences, right? That you can like go, you know, we can go say, okay, which one's which. But if you know, this and like was asked to me last time, this is not something where, okay, you're curving space-time so much that you get these non-linearities and other things. It's the mechanism here is reduction of inertial mass, but it doesn't the curvature of space-time in a quaternionic nature doesn't go away. It's still there. So it's just more complex and more nonlinear. So when I'm asked about the predictions about excuse me, Einstein's theory, the way I look at it is that this theory will predict the same thing because Einstein's equations falls from it, but there could be extra effects that if we use the full theory, we might find.
Yeah. What do you think about the vacuum catastrophe?
The vacuum catastrophe?
Yeah.
Well, yeah, that was one of the one of the reasons why, you know, quantum was the explanation was kind of gives us a pause, right, about the previous explanation. So yeah, I think that's an important thing to keep in mind.
Yeah. So yeah, we can connect. Not that I have a lot of time on my left with everything I'm doing right now, but I already have a GitHub account, so maybe we can connect at some point.
Sure.
I'm a C++, but I'm just warning you, I'm more of a C++ programmer than a Python programmer, but
oh yeah. Oh yeah, maybe you can help me because I'm trying to figure out basically all the libraries either have spinors and quaternions or there's tensors. There's nothing where it's combined like this. So you know, basically we need to figure out a structure where we could use this theory and it's in there in Python, and then people can start, you know, doing computations with it. Because once we get a Jupyter notebook with all of it set up, you know, at that point we could have it do what it needs to do, and then people can write scripts and, you know, do what they need to do to, you know, whatever they want to model based on the theory. So I'm just interested in getting the theory on there so it's accessible and in a place where you can actually do computations with it using our computing powers that we have nowadays that they didn't have 40 years ago or 50 years ago.
Yeah, exactly. Are you focusing on at the quantum level or the macro scale?
I would like to get basically all of the theory on there, including, you know, the Einstein-Sachs equations, which is the more general, but also the inertial mass field equations need to be in there. I think you need both, right? You need both sides of the equation in there. In addition, the electromagnetic part of it is really important because there are aspects to that where although the Sachs equations do have those variables in there, I would put it this way: it's sort of easier to, if you're trying to solve Sachs equations, it's easier to solve them like you were doing the Einstein field equation. So you can do a Schwarzschild solution or a Kerr metric, right? But if you ask me to, like, okay, can you from this derive the Coulomb law? right, or go to something close to what we see in E&M, then I would have to, I would like manually have to go and make, do the step of making it look like the E&M equations, so that I could go on from there. So I think one thing about these fields is it's not intuitive what they really mean. You know what I mean? Like, they're quaternion fields. So like, quantum is hard enough. A spinner, you get spinners and you got complex numbers, but we can sort of visualize that many dimensions, and we can visualize a matrix and whatever. But with this, it's like, it's really hard to get a gauge. So I'd really like to be able to like do computations without having to have the physical, make the physical assumptions about boundary conditions and just see what the theory gives.
Okay. Yeah, I'm definitely interested in more. Well, I would like to focus at the quantum level, but yeah, let's see what happens. I'll shoot you my email somewhere in the chat, I guess.
Sure. Yeah, I'll put my email on there as well. So if you guys want to go over that. Now, the other thing I was gonna share with you guys, because somebody had this question. I think he was a previous speaker. I don't know if he's on tonight, but he was emailing me and asking me about the kind of cosmology type work that Sachs did, and what the consequences of that is. And I think I briefly in my talk last time mentioned that in Sachs's work he did cover basically the prediction of this theory is that you get a universe that has cycles where it's expanding and contracting over time, large periods of time. So that's kind of what's shown here. And if you linearize this and you take it for short periods of time, things look like you basically end up with the Hubble constant, right? At the first approximation, it's a constant, but over long periods of time, it will expand and contract. In addition, Sachs was able to derive a spiral structure for large structures of matter. So you get an equation that like looks a lot like a spiral galaxy, basically. So these are a few of the subtleties that come out of using the quaternion form of general relativity versus the standard form. You don't necessarily get this. Now there has been some people. I think his name was Cooperstock. He was a fellow that did some computational GR, and so he did show that you do get a spiral structure, or you can get a spiral structure for galaxies, and you get the right velocities that we see in terms of the velocity curve. That the velocity curves of galaxies was one of the arguments for dark matter, right? So I think the way I see it is the problem with general relativity is that it's kind of like using the Klein-Gordon equation and trying to describe spin and chirality. You don't get those, right? We have to factorize the theory and get other predictions. And so people are like looking at, things and trying to say, okay, well, it's in there. It kind of is, but it doesn't come out of the theory. It's not really explained explicitly. So that's one of the big differences. So those are the two things I wanted to cover. And then in terms of what was going on in the lab, I did want to share a video today. I mean, there's this is just something that was in our email traffic back and forth today. I just wanted to share this and kind of go over what this is for the people that haven't seen it. So this on the left here is the drive. You can see that brass piece that's on some bearings on these rods with some springs on each side, and then this kind of part right here is an aluminum holder that's attached to a torsion arm, and what it does, it'll go back and forth when and you'll see it moving when the device moves. So what we're doing here is on the left of this, you see this part of the brass. On the left here, there's a piezoelectric, And on the other side of the piezoelectric, on the other side of this, there is an aluminum cap. Now, this is not attached here. This is all free to move. Basically, the only places it's attached is one part of the center of the brass here is coupled, so that the device can move freely back and forth, right? And so like I said, the device will exhibit, so far what we see is the device exhibits a preferential movement one side versus the other when you have different masses. Now, this experiment hasn't been done in a while, where you take two of the same mass and you see no motion. So right now we have, like I said, aluminum and a big brass mass, but we have another device that's ready to go, and it's two brass masses of almost exactly the same mass, to the gram or whatever. And we're expecting to be able to run that and show that, it behaves differently. It doesn't push. But let me play the video. And it's right here. This is the tracker software, and you can see these targets. It's like actually monitoring the targets and showing, the motion here. And you'll see that, at the parts where, there's some spikes here, this motion gets pretty violent, and you'll see a motion where it actually is pushed. So that discussion earlier about, seeing something, well, here we're on a torsion arm that's free to move. So that one was kind of a little bit hard to see, but some of these bigger spikes, you should be able to see that motion go to one side. You can see that shaking there. You see that? Did you guys see that? And you guys probably can't see this text up here, but this is being done at, we have a, there you go, there's some more. We have a signal generator. It's set to 0.6 volts RMS, but it goes through this amplifier. So everything's increased. Here's another, this is one of the bigger motions, and you'll see this block move over here to the right. And the frequencies that are being pumped in here, in this case, it's 40 to 35 kilohertz, and it's a 10-second sweep. So, every 10 seconds, it'll sweep through that frequency range. So it's repeating. And we have another bigger event here. I sped this up. I think it's slowed down. There we go. You'll see that moves quite a bit. So I think this run was from, I'm not sure, but sometime in the last, runs 8 November 2023. I'm not sure if this was a recent run or one from last year, but I thought this was a good example for you guys to see. Any questions?
I have one. Does that signal software, does it display every node point into an equation, the signal you get?
The software being used is something called Tracker, and
Okay.
one of the other people on the team is using it. I haven't been using it myself, but I would suggest, I mean, I think it's open source, so you can look it up. I think it's by a lab in MIT, or it's done by either a lab or some students or somebody at MIT did it. And let me also, so it should be available. You should be able to get it. Let me share with you guys what a typical run looks like for us. I don't know if you guys have all seen this, but this is without the tracker. analysis. But here on the bottom left, this is a spectrum of what we're seeing in terms of the electromagnetic energy that's being put in. So we have some sensors of current and voltage, like right at the output, right before it goes to the electrically goes to the device. Here you see different frequencies, voltage.
Kurt, I think you need to start sharing your screen again.
Okay.
I'm just seeing you. So
Yeah, sorry about that, Curtis. I stopped your share when you.
Oh,
when
no
you brought
problem. No problem.
There we go.
Okay.
I see a rock. Now there we go. Now I see the presentation.
So, okay, so on the bottom left, that's the spectrum. Right here in the middle, that's the voltage waveform that's going in. There's a signal from the current, and there's also inside the stack of the piezoelectrics. There's also a piece that'll, like, when it contracts, it's like an accelerometer that'll like send a signal when it feels some compression. And then up here you have the blue signal is, I believe, the voltage that's being sent in, and the red signal is we have a sensor on the other side of the torsion arm that'll see when the torsion arm moves. So unlike the tracker data, we don't have this is not showing the the tracker data explicitly, but you'll see this is what a typical run looks like. I didn't select it for whether it was a good run or not, just so you guys see what we see in the lab. And then later on we kind of process this and compare it with what we have here. And you guys can see that aluminum end cap right there. You can see that pretty clearly. And right now it's in a box with there's a piece of a plastic or something, kind of keeping it so that in case there's any air currents or whatever, it's nothing's gonna come out. So anyway, that's what a typical run looks like. That's it. Sure.
Awesome. Thank you. So let me ask who has questions for Curtis. And I know we've had questions kind of come and go. Jeremy, go for it.
Yeah, I think it's just more of a statement. I think the best measuring equipment you got for that device is probably in my opinion, just strictly in my opinion, is the accelerometer, since it detects kinetic physical interactions, like you move your hand to push something, right?
Well, so that is like a piece of it's not piezoelectric, but it's something that, like, when it gets compressed, you see a voltage. So I would say that it's hard to, because that's seeing compression regardless of when you're getting a piezoelectric vibrates, right? So
yes.
It's in that stack, so it's going to see that compression. So it's more of like I would say it's more of a verification that the energy is going in and mechanically doing what we expect.
But it's mechanical, and it's just pure kinetic, though, like any gyration detection, like of any gyration movement, or that would
no, it's just like when you compress the thing, that's my understanding of what the material is in there. Now what we're trying to do is we're trying to separately let the device kind of move on its own, and separately observe it moving. Now, one of the issues I have is that this is on a torsion pendulum, so it could be going back and forth. And so when you have nonlinear motions, a skeptic would say, well, you have all this nonlinear energy, and you have all these vibrations,
yeah,
and binding and letting go and doing all sorts of crazy things. So
yeah.
What we're looking to do is show clear push over time. So we're trying to fine tune the energy we're putting in, because right now you see the sweep is a pretty long sweep, and so we're going in and out of resonance in long periods of time. So we're trying to figure out, okay, the trick is, as the device heats up, the resonance will move, it'll change frequencies. So we gotta get a device, characterize it, and try to see if we can send a signal in that'll follow that frequency as the device heats up and give a good push for a long period of time. And the higher the push, the better, right? So
Yeah.
I think that's kind of what we're trying to get to. And then down the line, what I would like is I would like a experiment where it's on a linear rod where you're just seeing it move in one direction and that's it. So that would be what I prefer. Also, we're using this in the vacuum, so it's tricky to have, you can have air bearings like out in the air, but then you could have air effects, right?
Yeah.
Move. So what I'm searching for is some bearings that I can use in the vacuum. Because if I use magnetic bearings, people will say, "Well, it's magnetism." So we still might do that, and like there's ways to exclude the magnetism, but I prefer to find bearings that are we're able to use that can go in a vacuum.
Yeah, like would stainless steel be good as material?
Well, maybe it depends on the friction of the bearing. Hey guys, I need to grab a charger real quick. I'll be right back.
Dun dun dun. Cliffhanger.
Why wouldn't bearings work in a vacuum chain? See why there would be any problem with any kind of bearing work.
I guess it would mess with the signal detection or something. That's the only thing I could think of.
What, the bearings are squeaking or something?
I don't know if it would give false readings or not the actual material itself within the vacuum. Like I'm thinking because it's given off, like if it's magnetized, it's given off the magnetic field of the bearings, and that's messing up what you're trying to analyze without any, I guess, repulsion in the vacuum. It's putting stuff in the vacuum, whichever it'd be.
Well, there's ceramic bearings
that might work. I'm thinking like the higher the grade and material, the better thing you could do where it'd be good in the vacuum. Like I guess I don't know. I'm gonna stretch it. Like if you could get silver bearings, I mean, would that be good?
I don't know if silver is magnetic or not. I'm trying to avoid
it. It shouldn't be. I mean, it could be. It vibrates at a very high rate. So, like to me, how I see it. Everything is magnetic, but it just depends on the amount of hertz the object is vibrating at. And magnetic is only when something is is attracted or will push something away. So
yeah, two things: the frequency and the volume density.
Yes.
Yeah.
Anybody here got an explanation why a north field spins an electron clockwise and a south field spins an electron counterclockwise? Is there any simple explanation for why that is?
Not. I mean, it probably is, but it wouldn't be my expertise. I'm still a novice at this, but I'm just going off intuition and advanced material I had read currently the past 2 months. So, but other than that, I still need to read over the basics. So that's as far as I can get on it.
All right, I'm back. I'm okay now.
Okay. So I think Lulu had a question. Lulu, go for it.
Oh, where'd she go?
I put her hand down. She disappeared. Okay. Well, maybe not.
I think she's muted still.
Yeah, I hear her.
No,
can't hear you.
Maybe her mic isn't working. She's not muted. Yeah, Lulu, your mic isn't working.
No, we can't hear you.
Okay. Well, does anybody else have questions for Curtis?
Quickly refresh my memory, Curtis. What are you trying to detect again?
Oh, with the Mach effect experiment?
Yeah.
So basically, that experiment is something Jim Woodward came up with to show that Einstein was right about the Mach effect is one thing, but basically he came up with a way to use the Mach effect to actually push against the universe. So basically, in the theory, you're putting energy in the device is heavier while you push against something heavy, and then you're lighter, you push against something light. You'll kind of like that's kind of like the general way to describe it. You'll kind of like get a momentum in one direction, right? So you're pushing something heavy, you won't go that far, but when you're heavier, you push against something light, you go further, and so it's a way of like kind of moving you along. And what you're pushing against is the rest of the universe. In this theory, there's no background pairs. That's something out of Sachs's theory. It could be the mechanism for this. Like I said, I don't know. There's, I haven't done those calculations or showed that. But Jim has done calculations based on the Einstein and subsequent solutions or boundary conditions that he imposed.
So it's a Mach effect detector.
Yes, it's a Mach effect drive.
Can you guys hear me?
Yes.
Yeah. Lulu, what do you have?
Okay, I have two questions, maybe a few. Units of measurement. What are like, what are you using what is the metric, the units that you're using to measure the waves, the different oscillations?
Oh, in the Mach effect experiment?
Yeah, the one where you had the grid and you were showing the three different, lines.
So right now, most of the units that show up there are in volts or millivolts because we're using circuits and other things to detect those. And there's like somewhere there's data where we can like take those and like figure out, okay, what does that push really mean? Like how far away is that? So for example, the sensor that senses motion, like it's been like just about a year or so ago, a year and a half ago, I had that and I was measuring, okay, how far away is it, what's voltage am I getting and how far away is it from the surface? So I did a calibration. So it just depends on what the sensor is. Like every now and then it gets calibrated. I would say that some of the circuits that like are embedded in the torsion arm, we haven't calibrated in a while. I'm not sure when they were last calibrated, but yeah, most of those are in units, and we'd have to do a calculation to give an actual. Most of those are in millivolts, do the measurement, but we'd have to actually know the conversion factor to get the actual amount.
So you have equation of narrowing them all the different frequencies into different equations where you get this thing, this color, let's say the red ones that you had would be this equation, this one would be this equation, and the equation is basically the circuitry, like the combined
some of them, it depends on what you get would depend on the circuitry. So for example, that measurement device that measured distance, basically I've taken it and I put it on something where, I have a scale there and I can see what the distance is and I would see the voltage and I jot that down so that we have a calibration so that when we see on the graph, we're using something called picoscope. They have hardware and they have software that, you can use in a lab. And so that's connected to this equipment. And that's where the graph was. That's what that was. Now, there was another graph, which was the tracker data, which just takes the raw video, and we put registration marks on it. You saw those little white things with the little dots. I basically made those with one of those label printers, right? Just put a period and cut it. There you go. And so those registration marks are what the video, what tracker data is doing is looking at the video. Now, the video here, most of this is 30 FPS. We're trying to get higher to 60. I do have a camera that can do 500 at lower resolution. But some people have mentioned, well, you're at tens of kilohertz, you need to be able to see that motion, right? So if this is successful and if actually we can show a push and people start to get interested and we get funding, then maybe we can get one of those high-speed cameras one day. But right now we don't have that set up.
So, but like your transfer, you're converting though at the end of the day digit to a display that we are seeing. So there's also that, part of the conversion. It's not just what you're reading on your, little machine for output, but then, for like the display part, that also has its own conversion.
Yeah, so that's what I was saying. And maybe one of these days for these open mics, I'll be at the lab and I can show you guys what's in there. But we have that picoscope hardware that is hooked up directly to what you're seeing. So for example, that distance measurement is directly hooked up to the picoscope hardware, and it's pulling that every couple times, however frequency it is, a couple times a second. I don't know how many hertz, because there's different. Some of those signals are frequency signals, and they take a little longer. Some can be pulled much quicker. So it's like live data is being shown on the screen from all the sensors. And
Okay.
like I said, the scale is just shown like, okay, this is the scale we see, and you'll notice it's millivolts, and we know from the color coding which sensor it is. And we can, calibrating that or looking at old calculations, we can figure out what does it mean, like physically, like voltage. Even though I had a current thing, it showed voltage. Like we can go back and say, okay, what was that peak to peak? And we can go back and calculate that if we needed to.
Okay, but do you monitor certain patterns, like between the time, distance, or whatever, that I understand that you're measuring but like the units would be, let's say, this like distance between one to another, like whatever, however you end up like making it bigger. But what would that, like the common denominator unit that everybody would agree on, that this means.
That would mean that there's an effect.
No, like the scaling part where
scaling part.
Like, yeah, the everybody in the room, when they see, they agree on, we all agree on all of this. This is a agreed upon measurement, for accept, because measurement on different things, it's just, it could be read many ways.
Right. So for that, we would have to do like a caliber. Okay, so as my day job used to be a control systems engineer. So when I would set up an instrument, we would have a calibration, and the calibration always had NIS traceable. So basically, if we're really saying, okay, this is this much, and it's important, how accurate we're being, then you would want a calibration that's like independent calibration, and it's a certified calibration. So right now, we're like, for example, we're getting a new pressure sensor because the ones we have now are like really old, and they're not.
I had that next on my list. I had right here. I had it next on my list. And the next question: pressure plate and the vacuum sealed chamber where you have this. Yeah.
So the pressure system was something we were working on. We have all the hardware in there, and it's actually right now being pumped down. So I do need to. We did order a new pressure gauge that can get down to somewhere 10 to the -6 torr in that area, and we do have a cold cathode gauge. I just gotta figure out. I haven't found there's a coax, because the cold cathode gauge has a pretty high voltage. So you can't just use any coax. So I need to find a coax I can use with that. And so I'm going to be calibrating that as well against the gauge we just got. So the gauge we just got is new. We're still waiting for delivery for that, but that's calibrated by the manufacturer, right? So in the future, as we, as time goes on, every now and then we'll want to send that gauge to a calibration shop and pay them to, do a calibration and send it back, right? So to answer your questions, like to do that kind of thing, you would have to have, in my opinion, you would have to have things calibrated versus a standard so that you can show that, okay, here's a third party calibrator, and we've done, they've agreed and certified it and show some paperwork. That's the way I would do it.
Or you get another gauge and you leave the old one for reference on the
Right.
difference between whenever it gets calibrated every time. Because
Yeah.
if you lose that one and then you get a good reading and then you had it already preset, then you're like, oh, what did I do to myself if I only left, So you leave that where you think, and then you get another one where you get that, like update of the calibration, whatever their a unit now is of agreed standards, and then but you always leave your old to compare. You don't
Yeah, you can do it that way as well. The thing is, we don't have a lot of funding, so we have the equipment we have, so we're trying to get by. And a lot of the circuitry that's in there, and it's not showing up on that graph. So there's other things, but that do other things. Like, for example, there's what we call a calibrator's positioner, kind of, where there's a couple coils where we can move the arm a little bit so that we can center on the graph that we're taking of the position. So that coil, for example, we can use that. We call that a calibrator, but that's basically a positioner that it has its own circuit, right? So there's a few other things in there that are like, there's circuits that are hand built that do different things, and those aren't calibrated. But the big thing with this is, I think having a video is good, because the video is like an independent measurement of the position versus the position measurement we have. And if those two coincide and show that there's a push and we're getting what we expect, then we might get interest to like move on and do a linear. I prefer, like I said, a linear motion where you're not going back and forth. Like, that's the goal in my mind. And in addition, I would like the power source on there too, and the drive on there too. Like right now we're driving it externally. So that's kind of where we're at.
All right. Thank you.
Sure.
I have a question. Is calibration really necessary? I mean, can you do measurements without calibration and still get like the actual resonance of the old whole entire equipment itself and still do like accurate readings? I mean, or
for example, the pressure gauge, I put it on. I had the roughing pump, I had a turbo pump, and I put it on. There was it's a Pirani gauge. And so it got down and it went past 0, and the turbo pump kept ramping up. It wasn't at full speed. So basically I calibrated and set it to 0, because you can kind of guess that it's gotten pretty much most of the air out at that point. So, but that's not calibrated against anything other than, I have these pumps and I'm guessing, right? So having calibration is important, especially if you're going to publish, and the data is important to what's going on. So I think the fact that we're getting a gauge that was recently calibrated is going to be important for us to be able to write a paper and say, hey, one of the things that with this experiment is it was an error, and it was shown that what we were optimizing for previously was air effects. And so that we don't want that. We want it to be in a hard vacuum, kind of what Drew was. Drew has a pretty, the vacuum he had is a pretty good vacuum, and that's important to show that it's not the error, because error can, like I said last time, there's a helicopter on Mars, right, and that has a very low low pressure, so that it's important to do these things in the vacuum.
Yeah, I can see your point about that. But if you were to factor in the air and then solve the resonance problem, just see theoretically, what would that mean, even with air effects? Like you factored in the air coefficients with the resonance of the device, and you say you solved it. What would that mean, though?
So just to give you an idea, we had my professor Hal had I think another student run a COMSOL simulation with this device and show that at resonance, the air would give it 1 Newton of force. So you don't really want to run this in air to show a Mach effect. I mean, it could be that that if you put it in an enclosure and had the right, you're adding weight, right? You're maybe blocking the air because it's kilohertz, so it's like in sound frequencies, a little higher frequency than that. So it's hard to kind of block sound energy, right, without a vacuum. So I think for the experiment itself, air is a problem that we want to avoid at this point.
Okay. You're helping me out with my own research, what I'm trying to do, and just factoring like minute things. I do appreciate it.
Sure.
All right. Okay.
It's like HK.
Yeah, HK, did you have your hand raised? Did you have a question? He might have stepped away.
No, I didn't hit the right mute button. Is the thrust still in the micronewton regime, or has it moved up to at least millinewton?
I don't know yet. Now, when you say still,
I mean, the last I read, it was down in the micronewton numbers.
Yeah, if you were reading back when it was on a pendulum out in the air, then that more than likely was the error. So right now, I think what we're seeing could be in the micronewtons, like close to a micronewton, but it's really hard to say because of the nonlinearities. You saw how that moved, right? That thing moves, and how can we tell if it's like one's moving this way and then conservation of momentum, right? So and is it binding at the right time, loosening it up, and then going in and the spring pushes it back? We got to do more work and get the signal where we're like getting consistent effect, because that has been seen before. But the problem was it was in a vacuum that was a few torr or millitorr, and that's still not low enough. That still allows for potentially there to be air effects causing the motion.
In other words, a very dirty signal.
Yes. Yeah. So I personally would
known as distortion.
Wait and see.
Okay, thank you.
Awesome. Well, guys, thank you. So we're at about 6:43, and I'm not sure how you guys want to do things. Should we wrap up shop around 7 tonight, do you think?
Can I present something very quickly?
Yeah. Do you want to do an update, Phil?
Sure. It's going to be very quick, as I really ultimately want this to be archived. So just let me share my screen. Share screen. Brave browser. Yeah. Okay. So that's okay. Yeah, I forgot that Zoom they got tabs on in the middle of the screen. So just 1 second.
Unable to connect with server.
To read right here. Okay. All right. So I'm gonna reload my own page. So this is my YouTube channel. I did some experiment. Well, actually, my theory predicted that that a magnetic field will be responsible for time dilation. Then 2 weeks ago, I think I started looking for evidence on that, and apparently, I'm not sure if you presented very quickly the fact that if you put a magnet next to a plant, the plant will grow faster. I also showed a peer-reviewed paper saying that if you increase the Tesla field, then the time rate will increase as well. And I decided to do some home experiment on that. And it's still preliminary experiments, but you know, we're getting there. So I used digital clock. I put digital clock next to a magnet and another one away from the magnet. And the one on the magnet is actually behind the one on the table. So you can see that the clock on the magnet is a little bit late. And 72 hours after, I let the clock running for 3 days, and 72 hours after, then the clock on the magnet is actually ahead. So there you go. By 1.6 seconds. So again, this is a preliminary experiment. I was told by some physics expert who is my own boss to use different clocks, to use different brands, and that is what I did 2 days ago. Now these clocks, you can see they're perfectly synchronized. Well, we see badly the one behind, but they're very perfectly synchronized this time. And the measurement I got from yesterday, the clock on the magnet is ahead still, but not by 1.5 seconds, but by 3 seconds. So you see the clock below on the table is shifting to midnight right now. And yeah, you can see that the clock on the magnet is way ahead by 3 seconds. And now today I left the clock running, and the clock on the magnet is ahead by 6 seconds. So again, this is preliminary. I mean, there could be a lot of factors playing with the chips, the electric circuits, and so on. But you know, if it looks like a dog, it's quacks like a dog, then it must be a dog, you know. So we're getting there. Me and Sergio, we're trying experiments in our own little group. I might use a non-magnetic oscillator, or I might wrap the clock with a mu metal protection to confirm that time is really, that the magnet really emits two fields. It emits like some sort of frequency that changes time, and you know, the charge or a Coulomb. So it's probably emits two different fields, but in our mathematics, we're unifying these two fields as one field. But so far, it looks like a magnet is contracting time. So once it's going to be fully scientific, then I'll be able to publish the results once and for all. So yeah, thanks for your time.
Philippe, is that electromagnet or just a regular magnet?
Yeah, look, we got hands up there too. Let me go to Jared first. Jared has been quiet.
Hey, excellent work, Philip. That is some really cool stuff. I have two questions, or a question or comment. So the first question is, the magnets, the electromagnet coils that you're using, what are the parameters for voltage and current and magnetic field strength?
Yeah, these sorry, I forgot to mention, I'm using the two permanent ring magnets, neodymium ring magnets. So I'm not using a coil there, so it's pretty easy to reproduce actually. Ideally, I would have an atomic clock because it's pretty independent. It's pretty it's not affected by a magnetic field. But I don't have these labs yet, so I'm gonna use a Mu metal box and see if the time flow goes. It should propagate transparently from across the Mu metal.
But so do you have how many Gauss or how many millitesla the field is at the position of the clock?
Yeah, one ring magnet is 1.4 Tesla. So I have two of them. So I don't know if it's 2.8 Tesla, but something between 2.8 and 1.4.
So that was the first thing. And then the second thing, so I just learned from the Y-Files episode on Thursday about the time travel dude from Art Bell's thing, Mike Markham, and his setup. He ended up claiming that he produced a time travel type of device using extremely high voltages and extremely strong rotating magnetic fields.
Yeah.
Yeah. So his what I'm trying to get at with his thing though is the velocity and mass of the thing that entered the field determined how far away it would move from the device and how far into the future it would go, and that it could only go forward in time, not backwards in time. The numbers though that I think would be useful for your calculations here, if you end up determining the relationship between magnetic field strength and time dilation for your device. The numbers for his device, he was using somewhere around the ballpark of 3 megawatts, 3 million volts at 1 amp, and rotating magnetic fields of approximately 30 hertz and about 8 Tesla. And with that, a 1 kilogram object traveling at about 14 meters per second would travel an hour or two 100 yards away, whereas a full-size person following the same speed traveled 800 miles and 2 years. So it might also be worth observing how implementing higher voltages, or instead of stationary magnetic fields, rotating magnetic fields, might also interact with your device once you have it shielded.
Yeah, actually, but you know pretty well I have my own theory, but it's not a theory because I don't invent anything. So I'm just linking the electric field with the gravitational field and the magnetic field with time potential. And you know, that's the reason why I decided to put a clock on the magnet. But I don't know if there's a correlation between, well, there is a correlation between time and gravitational acceleration, because you can slow down a gravitational acceleration. But to give you an idea, there are direct link between the electric field, gravity, and magnetic field and time, where one induces the other in motion. So sorry, what was your question again?
I was suggesting other things to include, specifically rotating magnetic fields. You could also try flipping the polarities of the magnets to see if that also changes it. But in any way that you decide to go about doing it, messing around with what you're doing with these magnets to try to see if you can create a variation in the effect.
Yeah, that's what I'm trying to do. I'm gonna try to with the Mu metal box at some point and things like that. And the guy Didic on WhatsApp suggested actually to put magnets repelling each other and put the clock in between and things like that. So yeah, there's a lot of things that can be done. So that's pretty it's pretty interesting, because if you can slow down time or speed up time, then you can create easily force fields. If you slow down time, then you can stop any projectile coming at you. So that that there's a huge potential right there. Yeah. Thanks.
And thank you, Phil. Let me go to Curtis next.
Hey there.
Curtis?
So, yeah, so back about 12 years ago or so, there was a experiment being done in Europe. I think it was in Italy, where they had these particles. And what they did is they took an atomic clock and they drove it to where the receiver was. And then they shot the particles to the receiver. And based on the atomic clock they drove over there, it was looking like the particles were traveling faster than light. And of course, that was made big news. And at the time I was at UC Merced. This was before 2011, because I know that's when I left. And my professor came to me, he's like, Curtis, what do you think of this? And I'm like, well, how did they do it? Like, how did they get the time synced? And he's like, oh, they just drove an atomic clock. Well, you can't, like, so I'm bringing this up because you brought up an atomic clock, and what I did at the time is I found a thesis that I think it was a Caltech fellow. So Caltech has a thesis library. I don't have it off the top of my head, but he basically took an atomic clock and took it in a plane, took it like and you can see that every time the thing had some kind of acceleration or some motion, that the time was like changing. Okay, there was like little variations. So it's a real dilation is a real thing that can be measured with atomic clocks. Like you can actually see that. So I just thought I'd throw that out there in case you're interested.
Yeah, somebody else told me that the clocks were not at the same altitude. Actually, they're like 10 centimeters higher, so it might affect atomic clocks, but not these clocks are not precise enough to manage.
Yeah, it's not the height as much as driving it there, because when you're driving it there, you're making a left turn, a right turn.
Yeah, that's right.
All those accelerations, it's kind of anti-intuitive, but if you see that paper, the guy graphed it all out. Like you could see it clear as day. Oh, here's the plane taking off, and here's the variance in the time, and it comes back and like it's this far off, and it's really interesting. And actually the work he did was the foundation of what we have for GPS. So with GPS now, if you look at the GPS equations, they actually take into account the time dilation and the time it takes for the signal to get to us.
So it's really acceleration or speed?
Acceleration will change it. Like if there's a change in motion, you get the equivalence principle, right? So what I'd be interested in you doing is like having something where, okay, if you're saying locally the time is changing, like how can we measure that? Maybe with an atomic clock, that'd probably be the more local measurement, because a GPS measurement is like a global measurement, right? And you're adjusting for relativity. So there's a lot of assumptions there. Also, I would say if you're using any kind of semiconductor devices, those will have variance and they'll vary how they behave in magnetic fields. So I would be careful with semiconductor devices because there could be variance.
And a sand clock.
Yeah.
Yeah, they are anti-magnetic stopwatch, but they're watches actually, but they're like $2,000. They're not cheap.
Yeah. Well, if it's okay, let me go to Jeremy and then Gerald after that. Jeremy, go for it.
Yeah, I could add to that. There was another experiment done in 2011 on the History Channel called the Unveiled Files. I was watching. They managed to capture it. This is related to the experiment, but they managed to capture a UFO they had caught that was gyrating left and right. And it was a clear day. And later in the episode, they talked about that this independent researcher took a laser. It was colored green, so it's probably like near in the infrared maybe. But they went to the Cliff Dweller Anasazi ruins, where the four corners of Nevada and all that, the ruins in the cliff and those magnetic pools where they said people disappeared. They think that the theory was time dilation. Those pools are producing a weird magnetic field or something, or different fields that, like you said, time contortion, or time dilation. Well, the guy put got one side of the pool, say the north side of one of those pools, put the laser there, and he had a receiver on the other side of the pool. And when they shot the laser through, they did a second counter. I guess they had one of those watches, like you said. Because I'm trying to remember, but it was counting to like 45 seconds, and that they said that the laser or the clock somehow managed to detect, like the clock was built in with the laser to measure the frequency of the laser going through the particles. But for some reason they said that the clock jumped from once it's reached 15-second counter, it jumped up to 30 instantly. Like it skipped over like 16, 17, 18, 19, 20 seconds. It just went straight to 30 in 1 second. So it was the weirdest thing. And they said when they received it, they tested that the pool did have some type of time dilation. So that was kind of interesting. And later I tried to look up the episode, and it looked like it got removed from their channel episode log. So
they took it out or something?
Yeah, they did.
Yeah.
But that was an actual experiment and measuring laser frequency, time dilation, or laser basically, or laser particle type thing.
Okay.
So
yeah, well, let me go to Gerald next. Gerald, go for it, sir.
Hey everybody, I was wondering if you wanted to see a fun little demonstration of my vortex coil.
So Joe,
It's like a minute long. I'm just gonna show you what I'm doing. I've hung
so
up
I'll tell you what, why don't we do that? Gerald, can you turn your camera on, and you're gonna have to share screen. You're gonna have to share screen, buddy. And then so after that we'll go to Andrew and then Bill Alec, and maybe we'll close things down for this evening if that works. There we go.
I just gotta set it here. All right. Can you see the magnet? Oh. Okay. It just figures when you're on live, everything goes wrong all at once, right? So how do I share screen?
No, you are. Oh,
well, I am already?
No, you're not actually, but I can see what you're doing.
Okay, fair enough. What I had set up here before this fell off.
Yeah, I don't think you need to share. I think this is a live experiment. I think you're good, man.
Live, everything always goes wrong at the last second.
Nah, live is. It's the thrill of not knowing, right? It's the drama.
Right? I love it personally. Okay, so here's what I got. I got a 750-foot bifilar round vortex coil. I have a vortex generator pulsing through a horizontal deflection transistor. I'll be pulsing at 261 hertz. And the power supply is a 24-volt, 2-amp wall plug power supply. But what I want to show is the control of this magnet in the center. So here we go. Hopefully everything works properly. Can you see the spin?
Yeah, it's actually a magnetic vortex you're doing.
And I can control it to a fine-tuned rate. But if I push it too much, it sucks it to the outside. Because what it wants to do is it wants to come up and continue out. And there's also a vortex on the outside, but it's going in the opposite direction. So that's just my fun little experiment. I just wanted to show a magnet on a string spinning around a vortex coil.
That's awesome, Gerald. Thank
That's
you.
it. Thank you for your time, guys.
In the future, you should do it with one on the outside and one on the inside. We'll see. Maybe you can demonstrate both. And you know what the other
experiment.
Gerald, the other thing that you might consider is iron filings on paper, right?
Good idea. Maybe if I can get one of those gel type situations where you can see
or just plexiglass, just a piece of plexiglass, and then put some iron filings on top.
You know what? I'll try that next
The
time.
gel things aren't as good as iron filings. Put the iron filings inside of a salt shaker and pour it on top of either like a sheet of plexiglass or just a piece of paper or something like that. We'll give you.
There's a little toy that you can buy at the toy store. It has those little like tablets already. Like the filings are gridded. All you need is a magnet to like show the image. Like, you know, just take the plastic off and put it on there, and it could measure it.
Well, thank you for the suggestions. We'll do that next time I get the opportunity.
Thanks, guys. Okay.
Thanks for your time, guys.
Absolutely. Well, let me go to Drew next, and then Bill after that. Okay, there we go. Drew, are you with us? There we go.
Yeah. I just wanted to show that high vacuum is not for the faint of heart. How do I go to full screen? Do I have to share or?
Yeah. Yep, just do screen share, buddy.
Okay, so I want to screen share my main. I want to share my camera. How do I do that?
It should be the share button, and then it will that, or you could I mean, if you have this other camera plugged in, I'm not sure.
No. Okay, I don't know what to tell you. See this bucket? I don't know if you can see it or not. See this bucket of sad aluminum stuff?
Yes.
That's what's left of a $10,000 turbo pump that had a bad split second. High vacuum is not for the faint of heart. Very sad.
Well, thank you. Thank you for sharing that. Thank you, man. Let me go to Bill.
Yeah, Tim.
Yeah.
Yeah, in regards to what Philip was speaking about, using time. A number of years ago, I did quite a few experiments at a place called the Mystery Spot. It's located over there in Santa Cruz. And there's also another phenomena there called the Oregon Vortex. These places are for real. So if you want to study them, you can do so. A psychologist wants to write them off as, just a mental thing, but it really isn't. You can actually measure that phenomena. And I studied it in quite a bit of detail. My timing instrument that I used an Accutron watch, okay? Because the watch had a vibrating tuning fork. These watches. They were made a number of years ago. I think they're still available on the internet. And it makes a great sensor for measuring time. And this type of phenomena, they specialize in what they call shrink-grow phenomena. Okay, so as you walk into this phenomena, or this vortex, they call it, you'll observe that you'll start to shrink. Okay, but the problem is that if you have any sort of measuring device, okay, like a ruler or a yardstick, see, that's going to shrink with you. Okay, so the only way to measure that shrinkage or the growth phenomena is to use time. Okay, but you have to develop the calculations or the equations to measure that shrink growth phenomena. Okay, but it is for real, and you can measure it. And I did develop a number of years ago instrumentation to measure that phenomena using the Accutron watch.
Yeah, and people can look that up. We actually have some of those on the Alt Propulsion channel, I think.
Oh, okay. Great.
Yeah.
Called
So
an Accutron what?
Yeah.
Is it a chord transformer?
Did you write a procedure? Did you write a procedure, Bill?
Oh, I developed the whole physics behind it. Okay.
So do you have a link to it? Because I live right next to that. It's like
you'll have to Google it.
You might have to go to the Wayback Machine, okay, to see my old website with that. Okay.
So
But
look, what do I look under your name?
Yeah, Google it.
But the thing is that yeah, you would have to use the Wayback Machine to see that that old website.
What was the website?
Now the researchers that recommended using that was, of course, Richard Hoagland. You know, I knew him a number of years ago, and also a researcher by the name of Bruce De Palma. Okay, he was an MIT grad. He did a lot of experiments in gravity. Okay, and using taking a steel ball and rotating it something like 20,000 RPM and observed the rate of fall. Okay, using steel balls, and he observed that they fell at a different rate. Okay, you observe a different mass acceleration effect. Okay, using steel balls. I did some research in this area myself using magnets based on what's called the Boyd-Bushman experiment. Okay, that you can take magnets, force them together, and then drop them, and that you'll observe a different mass acceleration effect than a rock. Okay, if you were to drop a rock. Also, I extended the Boyd-Bushman experiment using magnets, and I observed a different effect too. Okay, mass acceleration effect. That the opposing magnets fell slower, magnets fall faster, okay, than the regular speed of gravity. So, and then Bruce De Palma observed that steel balls spinning at 20,000 RPM fell at a different rate too. Okay. So there's a number of experiments with this sort of effect. So I just wanted to throw that in there with what Philip was speaking about.
Yeah, you gotta be precise to measure change in gravitational acceleration with a magnet, because you gotta have a pretty strong magnet if you want to change.
See, now another area that I work in is in scalar fields. I just gave a lecture in Europe about scalar fields a couple of months ago. And it's based on Tom Bearden's work. Okay, Tom Bearden's work. And scalar fields is really your gravitational component that we want to work with. And see, Tom spoke about two different types of scalar fields. Okay, one is electromagnetic and the other one's gravitational. Okay, and both of them can be found with magnets. Okay, there's scalar fields. And all that a scalar field is that if you take two frequencies and multiply them together, that produces your scalar entity or your scalar field. And that can be either time forward or time reversed. Okay. If it's time forward, it's gravitational. If it's time reversed, it's anti-gravitational. Okay. So that's how, if you want to build a flying saucer, you have to use the anti-gravitational component or the time reversed scalar field component to do that. Okay. So I just wanted to throw all this work in there into the mix.
Interesting.
So that's all that I have to say about this. But you can find my lecture, I think, on the internet here about Tom Bearden's work in with scalar fields and gravity and anti-gravity.
Yeah, Mike Faraday already suggested me to read about Bruce De Palma also, like you were mentioning.
Anything else, or?
I have a question. So it's like I guess you would to add to your thing, Philip. One more deal about time crystals. They said that even if a crystal is really small, like the size of less than a penny, the circumference of a penny, if like it's so small, like if the crystalline structures that are probably at the nanoscale, or between that and the microscale, I think, if the crystalline structures are shaped a certain way, and this has relation to the experiment you talked about, they would shoot a laser through it, and they said that when some of the light passes through the crystal, in some parts of the crystalline structure on the like really deep inside near the middle of it, they said that some areas in the spots in it, the light would actually travel faster than the speed of light. Like the light got accelerated, so it almost reached, you would say, like they said that it stopped gravitational forces inside the crystal, like it defied, like it had time dilation was recorded inside the crystal in the area where the laser or the light got really accelerated fast. So hence the name time crystal. So it's like shooting a light laser through some kind of density, and then for some reason, I guess depending on if there's not, I guess a lot of collisions in a certain part of the inside the object somewhere in some some location. I'm thinking of a plot point map, 3D, X and Y axis kind of grid thing, and it maybe a time dilation is occurring right inside the material somehow. So, but they managed to detect that, made books about it. So, kind of adds.
I found a link to that experiment you were talking about, Bill, and I posted it in the chat here.
Oh,
Thanks,
okay.
guys.
It's got your name on it.
Yeah.
Okay.
So I think if it's okay, why don't we close things down for this evening? Again, happy 3rd birthday to APEC. This has been a pretty kick butt session tonight. So, we have Sal Pies. He's going to be doing a presentation with John Brandenburg, I think, in about 2 weeks. And so we'll see kind of how things go there. We're trying to open things up. And then I know Mark, and Mark didn't do a presentation tonight, but he has been kicking serious butt with EPR research. We have a bunch of stuff going on. So let me close things down for this evening. But again, thank you so much for attending. This has been APEC Open Mic for November 11th. Have a wonderful weekend, guys.
Good night, everyone.
Awesome.
All right, good night.